Yeah,
Good
just
from our
assume
side, thank
everything's
you.
fine. Okay, perfect. Perfect, thanks. Colleagues, in front of you, Brian Nube from the Minerals Council. I'm the Senior Policy Analyst looking after safety and behavior. And it's my honor and privilege today to be Program Director and help, steer the ship, guide the conversations, and, hopefully come out with insights and actions to take us forward on this important topic of mud rushes in our SA mining industry. And, in the interest of safety as well, we'll start with a brief share on, safety, emergency preparedness in case anything happens in this venue. I would like to invite then patients from Silverstar to share with us our readiness in case anything happens. Over to you, patients. Okay.
Good morning, everyone. My name is Patience Tulari, the Health and Safety Officer for Silverstar. So in case of emergencies, we have two exits, the one on my right and the one that leads back to the floor. So the exit this side is going to take you to the parking, and then security will lead you to the assembly points. So in case of anyone not feeling well, We do have a clinic on site, so you can just shout to one of the employees here, they will direct you to the clinic. So we have our smoking area on that balcony, and the toilets on the other side of the foyer. Thank you very much for choosing Silver Star Center. Thank you.
For that share, patience. Yeah, colleagues, I think just to officially welcome us, I'd like to invite my partner in safety. I almost said partner in crime. That would have been incorrect. Mr. Dushendra Naidu, he's Head of Safety and Sustainability at the Minerals Council. Over to you, Dushen. Thanks.
Thank you, Brian. Good morning to everyone. Welcome to this day of learning on mud rushes and water inrush. It was a lot of preparations to get to this point, I'm sure, as you know, and I guess the importance of this day is really to get our minds around this issue. This is really a high-risk aspect of mining, and we've seen, I think there were 7 fatalities that came out due to mud rushes this year. Just to give you a perspective on fatalities, I think as many of you know, 44 fatalities to date. I've also heard of 2 recent incidents this week. We're still getting all of the details around that, and we usually lean on the DMPR and the provisional stats that we get on a monthly basis. So, but we are standing at 44 fatalities. I think it's about a 38% regression in the industry. So we've lost a lot of people this year, and as you know, each and every single person lost is one too many. I think in the interest and out of respect for all our colleagues lost, if I can just ask everyone to stand and acknowledge a moment of silence, please. Thank you. Thank you very much. When I speak to colleagues, it's always a very very similar response to how this year went. 2026 was really marked by quite a negative start. I think a lot of you would know the Minerals Council's involvement as well in some of the incidents, particularly the Kapa mud rush that happened earlier this year. This has left, together with all of the incidents, a real, it always leaves a mark on us as a safety, the MOSH team at the Minerals Council, and broadly as a member body and all of our members, safety representatives. So it's been a really difficult start this year. To address this regression, we did have a CEO heartfelt conversation on safety on the 31st of August, this past Monday. It was a very good session, very reassuring in the sense that we had all of the stakeholders in the same room together with our CEOs. So we had the union presidents there, the chief inspector of mines, and the deputies. It was very encouraging to hear the honest, courageous conversations coming out. And ultimately, the main goal was to look at a standing commitment to see how we can turn around the safety performance in the industry. So as a Minerals Council, we are working on this, on all of the outcomes, and we will release those outcomes to all the members, to all the stakeholders. There is serious commitment from all round, from all the stakeholders, including our CEOs, and you will see what will come out of that. We try to streamline on a particular committed action, and it's not far-fetched from what we are already doing, but it's getting that commitment from the top and also closing those gaps between the senior executives and the front line. Because I think many of you know, it's really when you're on the front line that one can understand some of the circumstances around mining, the complexities, being underground and or being even on surface mines, where the frontline are working, all of the risky activities that one has to go through. I think one can only really understand that when the leadership is felt and when you're on the front line with people, engaging with people, and seeing how we can help mitigate risk and prevent fatalities and injuries on the face and at the front on operations. I think that's a key thing. But in terms of mud rush and water inrush, a serious risk in the industry, we've been engaging with all the experts, and you'll see we've got quite a lineup of speakers today. I think that's the beauty of these days of learning. You get to meet some real experts around the specific topic with hardcore knowledge, really deep dive knowledge that can be shared and promoted throughout the industry. And I think that's the main purpose of this day, is to absorb all of those learnings. And I always say, if you can just take one of those lessons and apply it in operations to potentially lower the probability of an event happening or incident happening, that's already made a difference. So please, let's learn from each other. Let's engage. Some of our speakers are online. We have the honor of having Dr. Kim Morton here, who's really an expert in on hydrogeology and mud rushes and water inrush. She's also been a huge guidance for us as Minerals Council, an expert in this area, and together with others, from our mining companies and from consulting services and other stakeholder bodies to really engage with and to learn from. There is one apology, though, and I'm sorry to say that Mr. Manas Furi of Mine Rescue Services won't be able to deliver a presentation today, unfortunately. I've just had a call with Manas just about 15 minutes ago, and I must say the Mine Rescue Services are an amazing team. These guys are next level. They're really angels in disguise, and unfortunately, he couldn't make it today. It was due to an emergency situation that they had. And his crew are actually going through quite a lot from that incident. So I won't go into the details, but yeah, they've really went through a lot these past few days. There was a serious incident that they had to tend to, an emergency situation. So apologies from Manas, but I'm sure you'll hear from him through other forums. I've seen some of the presentations shared by the Mine Rescue Services. It's been phenomenal, the amount of effort that team puts in to save lives, and they also put themselves at risk. I've seen through the ICAPA ordeal how they've put their lives on the line to try and get to the people. And it's really remarkable how they put themselves out there. But yeah, we'll share more of that through other platforms like our Hours of Learning, etc. We'll still have those opportunities. So I'll leave it at that, everyone. Welcome to the session, and I hope you enjoy the session. So let's take away the learnings and let's start implementing. Thank you very much.
Yeah, thank you very much, Tushen. And please, Tushen, grab a gift. So everyone has a gift. Every speaker, there it is on the floor there. Sorry, Tushen. Yeah, thank you. Thank you, Tushen. Thank you so much. Yeah, colleagues, thanks Tushen for that opening and just sharing what this session is about, essentially. Next, colleagues, I'd like to call on Mr. Makete Tema. He's head of operation at Westwits Mining, and he'll be sharing with us about a mud rush incident at Kala Swallows, giving us a technical review. Yeah.
There's music in the background. We can't hear anything.
Can we take care of that, please, colleagues? That's
Thank
our
you.
online team.
Thank you. Bye. Bye.
All right. Yeah, Makadiva can use the podium. Okay. I'm assuming the team will just display his presentation. Do you have a presentation? Yeah. Okay.
All right. Good morning, colleagues. Thanks, Brian. I appreciate, and to the Mineral Council and all the industry leaders who are here today. So I'll be sharing learnings more than anything from the incident that we had, which was a mud rush incident. And I think, just to echo the previous speaker's words, it's been a very difficult year for the industry as a whole. We have seen a big regression on our safety performance, and it requires that we introspect and we look at what is not really working well and improve. And I always say that I think our next big improvement on safety will come when we use the information that we have more proactively, to try and prevent incidents and accidents from happening. So I'll just start by doing an overview of the company, just some update. We are a junior gold mining company. All right. So I won't bore you with the technical details, but this mine where this incident happened, Kala Shallows, is our first underground mining operation. And we started in the last couple of years, actually have a summary here of the, this is not working as planned. Oh, sorry, there we go. All right, so this has just been a short journey of the company. In the last 8 years, we've made a lot of progress, starting on the left to looking at an old adit mine that was mined more than 20 years ago now, to far right, bottom far right, where we are today, and we're operating, a gold mine in a shallow mining area. So this is just the layout of the mine, and I'll explain why this is an important slide. So if you can just look at starting on the right, or my right, you'll see we've got what I've termed there the North TSF on the lower side of the mine, and the mine facilities in between, and also have the South TSF on the other side of the mine. So the mine is basically sandwiched between two old TSFs. So, and then it's a shallow mine. We access underground workings through decline development, decline access, and in terms of the mining method, we do conventional stoping. And then there's the TMM that we use for trackless development. And we currently just under 500 people on site, most of which are contractors. The operations restarted just over a year ago. And we had since had our first ore end of October last year. We had our first gold pour in March. And we're currently in the ramp-up phase of the mine development. But unfortunately, then we had this incident on the 7th of June, just before midnight. And what happened was we had a reported mud rush incident where a colleague, while we were busy with loading operations, so the LHD was busy loading into a dump truck. So while the dump truck operator was waiting for the LHD to come back, we had this release of energy, a mud rush, started, and the operator attempted to escape. He left the machine, the dump truck, and in that process, he was overcome by the mud rush. So I will not be going into too many details around the incident because it's still under investigation. But I'll just talk to what we have learned and what I think are lessons that the rest of the industry can take, especially mining in areas that are shallow mining areas, where you've got historic workings in the vicinity of current mining workings. So the approach from our side was to look at the hierarchy of controls, and try and see what we would need to do to engineer out the hazard. Because, as you can imagine, the other higher, more effective controls are very difficult because we are in development stage, we are developing access to the ore body, so it's not possible to leave those accesses and go and start afresh. So we then looked at a process where we've covered, we had to, my pointer is not really working well, but we had to look at a process of different ways to gain information and gather information about the source of the mud rush, and also develop a remedial plan to prevent the reoccurrence of the mud rush. And that's the process we followed. So starting with the cover drilling, So we did conduct cover drilling underground, which was part of the mining program from the very start, that you do as you develop to make sure that you don't mine into surprises. So we did conduct the cover drilling as earlier this year, and all we picked up at that time was just water presence underground. There was no sign that there was material that would come into the mine. And then we also had a subsidence monitoring program, which was one of the risks we identified during the baseline stage of the mine risk assessment stage. And we have a program where, particularly on the site of the South TSF that I showed on the picture, we've got beacons that monitor movement of ground. And in this case, we had picked up around March that there was subsidence in this area, which was right just outside of the area where the beacons are installed. And we then went on to look at the subsided area and fill it up and redirect water. So the main reason for this subsidence was related to the heavy rainfalls we had in February and March. And then we went and remediated that by closing off the subsided area. And we, at that time, believed that we had addressed the problem. This was one area that showed movement. We believed that it was related to the rainfall, so we closed what we thought was the ingress of material into the mine at that stage. And then we also did Then we also did a survey of the same subsided area just to understand the size, how much material we had to put in, also, the coordinates so that we could also properly map it to underground, superimpose it to underground area. And that was all done, and that we closed off the subsided area. However, we still had the incident. This clicker is not working out very well, but anyway. So we still had the incident. And so at this stage, so this is just a section view, schematic view of the mine. So if you look at, that's where the South TSF is. And this is the area where we had subsidence. And then if you look at also not directly in line, but that's where the portal would be of the mine from a relative elevation point of view. And then we have underground workings. So the scene of the accident is sitting vertically below the area that subsided. So we filled the area on surface, and we believe that we had closed the ingress. But what was also clear from the hydrology study that we then did post the incident, it was very clear that there was runoff from the TSF. It's an old TSF that is currently not really being maintained. So there is material that runs off on surface and also in groundwater, running through into the mine workings. And how does that happen? So that happens through this complex geology that we then picked up, as we were doing the geohydrology study. So the intersection of the different dikes from surface, weathered zones on surface that are very oxidized, open up channels for material that does not only run on surface, but within the groundwater mass, found its way into the workings underground. So when we closed that void on surface, and we extrapolated its position to underground, what was not done at that stage was to understand that even below that particular area that was closed off, we had this area of intersections and confluence of different structures that created a pathway for water to go into the workings. But what we also did was we then took samples of the mud rush material from underground. We did the same from the TSF, and we found that from the lab, the material is exactly the same. So the challenge now was, how do we prevent this ingress of material, from coming into the mine? So the obvious starting point was the area where the mud rush occurred, which I'll speak to now. But it also necessitated that we actually had to look at the whole mine, and not just the one area, but the whole hydrological study around the mine, understanding where the water source is, to a point of extrapolating where some of these structures will be intersected at lower levels. So we are still at the first level of production, but we are already looking at, when we get to level number 4, level number 5, where are we going to intersect these features, and some of them, can we remediate them from surface? If they are very weathered, maybe there is an opportunity to look at, can we void fill, can we crowd some of these structures? So this is just a different schematic representation, almost like a heat map, showing exactly the same thing. So that's the area that we filled the void. But if you look at these greenish structures, these are all the dikes that we have on the operation, and the associated geological features such as faulting and so forth. So from the geohydrology study and the geophysics work that we have done, it was very clear that we had weathered geological structures that now we could interpolate. There was acidic flow of water coming from the TSF into the mine workings. There was also a very clear connection between, the potential hydraulic connectivity between the groundwater mass and the water mass from outside the mine. And the subsided area was directly above where we had the mud rush. So it was directly related to the area where we had the mud rush. So a combination of weathered and geological features and line surface water channels, increase the likelihood of water going into the workings. And then also surface water and stormwater management is important because, yes, you do have this source of water around the mine or around the area where you mine, but how do we manage stormwater? And we have seen very erratic patterns of rainfall. So if you have peak rainfalls, you can easily induce a mud rush, especially if it's coming from outside, like we've seen in the northern area early last year. So lastly, in terms of the remediation plan, so speaking to the area where we've had the mud rush, so we had to firstly go and assess the stability of this particular area from surface. Just don't have the surface boreholes delineated here. So we drilled around the area to determine, how stable is the area after the mud rush. If the material went off and it left a big hollow behind, so we needed to go and assess that. And we've done that, and from the drilling we've done, there was just, I think, 2 of the 8 boreholes that intersected very muddy material. So the area around this, just below this void fill area, there's portions of it that is, very weathered. And then the second phase of that was to come and do drilling also from underground to firstly distress the area so that we can access this particular void that was left by the mud rush. And, currently we are in the process of looking at what void fill material would be suitable for this type of area, without creating other issues. But the area is currently isolated. But what it also meant for us was that we could not only focus only on this particular area. We needed to look at the whole mine area. So in closing, firstly, it required that we use different sources of information for us to understand exactly, what was the cause of the mud rush, understanding the confluence of the geology, and as well as the nearby structures and their influence on the mining operation. And also to look at how can we engineer out this risk, on a more longer-term basis. And also, as I said, we currently conducting a hydrology study to try and plan ahead so that when we get to the lower levels, we already have done some work. Because it also has implications for our water pumping arrangements as we go underground and go deeper as well. So that's the end of the presentation. I don't know if we take questions now, Mr. Ngube, or there are no questions. Okay, no problem. Thank you very much for your time.
Colleagues, thanks to Mr. Makete for that presentation. Another round of applause. Yeah. Mr. Makete, is so quick in responding to this war we're in. I mean, we had a port hour of learning, Makete, the other day. And within that day, we had, a few texts And you know, we set up a meeting, and you met with our MOSH team, all our leading practices. You know, for me, that shows like how serious we are, you know, about responding to this problem we're facing. So well done to your team, and hopefully we'll have other engagements and sort this out. Thanks. Yeah, colleagues, I'd like to call our next speaker now. I see he's coming up, Prof, to take us to the next session. Yeah, so Prof. Matthijs Dippenaar from the University of Pretoria. I'm not going to read out your whole CV. It's going to be too long. Yeah, but I'll just leave it to you. Over to you. I'm sure the team will project your slides, and then we'll take it from there. Yeah, thank you. Over to you, Prof. Thanks.
Thank you very much, everyone. So I'm Matthijs Dippenaar. I'm from the University of Pretoria, and I'm there an engineering geologist/hydrogeologist. So my idea now is that mud rushes on nothing but mud is and slope failures and stuff. So it basically goes through that substitution and elimination that the previous speaker came from. And geotechnical is engineering geology, and geohydrology is hydrogeology. So we're letting go of the term geohydrology because both of those are geology. Okay, so my talk is basically here now today. Instead of I have some examples, but in terms of mining and everything, just give you a context of what the data looks like, what the problems and everything we need to do to actually better understand whether something can happen. That's why I think it was elimination and substitution from those last two. So this is basically building onto that. Okay, so there is some theory in there and stuff, but so I have this in there as a beginning. As I said, I don't work in mines, I work with mines. So basically, this is the case study that works there. We can now see this, I think, is on the agenda here. Okay, so that happened. So mud is a material that mobilizes. It's a geological material. And yeah, as I said today, I will run through a bit of theory and a bit of literature just so that you have it on the record. So that you understand basically what data we need to start addressing this. So just another little picture of that. Okay. So that's basically from Jakubec. So I got just some new references of literature about definitions and that for this. So not to necessarily run through all of that, but so this literature is available and I can share it. So basically those are the definitions of everything. Subsurface, and then this person's questions are, is there a potential to generate finds? So in other words, in the mines, that's part of what you do. Accumulate water, so that's why that's the second one, so the finds and the water. Can you form mud, and then can you mobilize or discharge it? Okay, so those are the two important things, or the important things. Which one is the pointer, the red one? There we go. Okay, so those are the 4 questions, basically. That's why I say my talk's more about seeing whether this will happen and how it happens and how to prevent it. So there's quite a bit of new theory, so I like this one as well from the same author. So that stuff there at the top, basically, whoopsie daisy. Just go back. So that one there. The top, the finds, that's basically the engineering geology. So that is where we look at where the material comes from. So in other words, when the work is done, where the soil or rock comes, and then that's the water that has to mobilize, has to form the mud. Okay, so all of that's now the materials that work through that. That's now another reference. INRAS has it, as I say, just literature there. So that you have some new stuff, but there at the bottom, that's the material that you need, rocks, finds, or water for it to mobilize. So every mine is very different with this, and have different materials that do this. So in other words, that's why I say, thanks to the previous speaker, this is in that green zones, hopefully, that this goes through so that you can start seeing what the problems are in your mines. So a lot of literature, but yeah, so occurs, there's the particle sizes. So this is now going into the laboratory tests. So 20% sand-sized materials. What if I shouldn't move to that side rather? See if it works better this side, because I don't need to see the screen. No, I feel better this side. There we go. So there you can now see sand size. So you need that coarse fraction, and then water up to that. And I'll run through a bit of theory just for you, those of you who work with this data. And then you need mud-forming material, water, mud, that can happen. and that. But you can see this is now different references as well. Okay, so the literature, as I said, I can show the articles if you want that, but it's summarized here. So those are the fractions that you need. So fine-grained materials and not saturated or near saturation, and we'll get to that as well. Okay, so it needs to be wet. That side is the same as the previous one, and that's it. Lastly, on this side, so let me walk back there so they can look there. So I know there's a lot of text, but as I said, that's more for you to just have it on record. Okay, so that's basically what causes it. Then finally, so this is hazards now. So this guy told me it's a recent article from last year. So there's now ways that he just looks at the hazards, and there's now where we now actually go into what we do. So in other words, when we describe materials, we need to describe what we call the texture, and you need that in lab results, but also in the field. So in other words, when your engineering geologists or geotechnical people do that work, they describe the materials. And basically what you see in there is that you have different things, so the grain sizes, and we'll get to that, determine whether it can happen. If we see colors or iron or stuff, it means that it has water and then openings. That's the other way that you can look at the texture size. There's the equations. Okay, so that's now just what people work with for you when you get the data. Okay, so engineers, last thing, that's what I want. They work with void ratios, and we work with porosity. So theory, that's now where it gets more important. Okay, so when you have someone now to describe your soils with, the more variety you get in your soil particles, the more it clogs the particles. In other words, the more water can go in there. So in other words, sands and stuff won't form mud. You need finer soils to do that. Okay, so when someone gives you the data, it will be different gradings, but you need different materials to actually mix. There were some animations in here that's lost, but in any case, so you need fairly that stuff that sands and gravels won't form mud. Okay, so there are now examples. So in the field, clays, for instance, will form mud. It's cohesive. Sands won't, so that's like beach sands. So just a bit of theory, so that's how we distinguish between these. For those of you who did soil mechanics or something, that's why in the labs you need this data to know whether you will form mud. So if something is only frictional like a sand, it won't form mud. It will only like sand in a desert or on the beach move. Okay, but if there's cohesion, so in other words there, so you have some strength in the soil, if it's moist, like a clay that you can squeeze, it can form mud. So in your laboratory tests, and there will be some more on that, you can decide whether that material forms a mud. Okay, and that's why I now say thank goodness for the previous talk, because it's about now the data that you get to look at that. There comes nice photos and everything afterwards, just now running through some theory. So that's now the difference between that. So that top one there, that's what a sand looks like. So there's nothing that holds it together, no cohesion. And the clay is different, friction. So in other words, if you have a clay or a fine soil, it can't just flow off like a sand. Okay, so in your lab tests or your data, if something is frictional, it can't form mud. Okay, so in other words, if your tailings are rock, it can't do that. Okay, so that's why just a bit of theory there. But then now something else. So in other words, where you get those mud is now anything that you have in your mine. And that's why in any mine you have different rocks, you have different ore and different gangue. So in other words, the rock itself can do it, or backfill that you use. So in other words, when you mine from underground or whatever, that materials or the tailing or whatever materials can form mud. Okay, so that's the sources of your mud that can form. And also something that weathers, like shales, associated with coal or kimberlite, can weather very quickly. So that can generate mud. In other words, your ore can decide that. Tailings impoundments can form this. And I have examples of that later. And then once again, backfill. So in other words, that's what we all do. And that's what especially engineering geologists do, the geotechnical people, is look at something in native state and then have to preempt what happens afterwards. Okay, and that's what you are now here for, because you change the environment and then you can induce that. Okay. So that's the engineering geology part, the source of the mud. Okay, so where does the mud come from? What does it form from? What the properties are? Okay, so that's the engineering geology or the geotechnical part in mining. Okay, so where does the mud come from? The next one is now the water. It can be rain, so in other words, the water that comes from the top. It can be groundwater that's underground. Water is used for drilling and operation. For instance, if you do percussion drilling, you have water in there that's going part of the drilling method. Or operation if you need to cool or something. And then water from leaks. And also then water can accumulate internal, and we'll get to examples. So that is when water gets stored that it wasn't in earlier. In other words, that's how the sources of water that can make your mud. And for minerals, internal and external, so water can actually accumulate per mud to discharge point. So now, once again, anything can move somewhere. So if you have a point where water exits, that can happen, and then the mud to discharge. Okay, and that's the hydrogeology. Okay, oopsie daisy. Where's the rest of my slides? Did I send you the wrong one? Oopsie. That's halfway in my slide. That was the boring part. Can I quickly take you mine? We have time. Sorry, that's a mess. That was just the theory. Oopsie. Luckily we're ahead. Yeah, I knew that would go south. We're just taking this one. What side? There. Yeah, do you have a stick? Yeah, take a 5-minute break. This will go quick. Luckily we're ahead of time. Yeah, that's the wrong side. I was afraid of that.
Cool. We'll continue now, colleagues. Matthijs has sorted out the slides. Yeah, I think we're all good now. In the next minutes, we continue right now. Yeah, no time, we're still good, luckily, so it's okay, no time lost. Yeah, yeah. Awesome. Okay, awesome. Over to you. Thank you, Matthijs.
Okay, so we'll start exactly when everyone's in. 2 minutes. Just by the way, the water on the tables are healthy. Actually, minerals in there. Okay, everyone, please come in. Continuing. I think you can put on where I ended off so long, please. People inside, still outside. Come in, please. Hoi. Thank you. Yeah, we're luckily made up time now, so I don't know what time I must end. Probably half past. Okay, everyone, so we continue. We ended at this slide. So in other words, there now you can see that's what's supposed to happen. So that's the engineering geology, and that's the hydrogeology. And that's why we split between those here. Okay, so the fines are the engineering geology and the water, the hydrogeology. So this is now from another side, another reference. More definitions, engulfment, inrush, hazard, overrun, blah, blah, blah. But the point that matters here, once again, what we work with is the rocks, the fines, and the water that you need to mobilize. Okay, so that's the stuff that matters for us. Okay, those three. For the other one now, there we go now, there, wet muck. Once again, I don't know the differences between all of these, but there's now in this reference all of that stuff. But once again now, really, there we go. So that's the stuff now that matters. The sand size materials, so in other words, the texture that I spoke about matters of the soil, and then the water that's there and stuff that can form mud. Okay, so just from all of these references now, it keeps on going back. The soil texture, so the particle sizes and the water matter. Another reference, those fine grains, saturated to near saturated, water, soil. Okay. Once again, I can share these references, the articles, if you want that as well, but this is the good summary. Another example, water may lead to ore compaction. So once again, as soon as you add water, this happens. Okay, so you've had anything, as soon as you add more water, we'll get to that, it starts to move. So lots of definitions here, and then there goes hydrostatic pressures. In other words, it adds to the pore water pressure. So when something gets wet, it can actually push the grains apart. Okay. And starts to move it, and we'll touch on that. So it changes that water pressures. Okay, so this I like. It's from that reference. It's a classification system, and once again, they're just different particle sizes. Okay, so once again, you work with it. So just some new recent references that make it quite nice. Okay, so this guy, once again, on the particle sizes. Okay, so that's now that theory. So now that's what we work with, and this is now where this comes in, because that's what happens to rock, is you can break rock by compression or tension. Okay, most of you know that, and cement and concrete have no tensile strength. But this is now where we are, so soils fail in shear. So in other words, soil has to do this. You can't pull it or push it because it's not stuck. Because all soils fail in shear, and mud is a soil. Okay, so all failures here fail in shear. Okay, so that's important for what we are now going through. There's just once again the basic theory, just so that you know. So when we look at soils, there are solids and there are voids, and those voids are filled with water or air. Okay, so basically the engineers once again use void ratio, but that's just the normal phase relationships. And now this is where it gets important. So permeability, or hydraulic conductivity is the ability of water to move through something. Okay, we use velocity in science, meters per second, because it makes sense. Now the point is, if something is water saturated, it's at the fastest rate, but if it's not, if there's still air in, it goes slower. And that's what this little graph is now showing. So if it's dry, there's no water movement. Okay, and that's now what this goes about. So when it's saturated, it means it flows at the fastest rate. Okay, so that we then calculate, and that then means it's saturated, so your porosity is water-filled. Okay, so this you can determine in the field or in labs, but the point is that you need to know this value because that tells you how quickly basically water can move through it. Engineers work in centimeters squared in permeability. Okay, so there's not just another way, and once again, whoopsie, more recap. This battery is funny. I don't know. Yeah, I think the batteries are flat. Let me just check. But, there's not a button here. Okay, yeah, there's no buttons. Yeah, more buttons, please. Okay, but then just to further, while they bring that, so basically what this now just shows is the more you wet something up, then the higher up the velocity of flow can go. Okay, so the quicker water can flow. And then based on that now, that just means that to be conservative, we always work with saturated systems to have the highest possible one. Thank you. Batteries, that's fine. No.
Are we able to move the slides from the back?
Yeah, can someone
click?
Yeah. Yeah. So that just, yeah, there we go. So yeah, thanks. Working. Awesome, thanks. Is it going? Not. Yeah, not. Yeah, otherwise just from the back I can show. Okay, yeah, let's just move. So that now basically there shows it. So that's the relative one, and that's the relationship between hydraulic conductivity and permeability. So that we basically call the fluidity, which is the unit weight divided by the viscosity of water. Okay, so in other words, you remove the water from the equation to give permeability. Okay. Click. So that now just shows it, and once again, I don't know if you know this, but now here, that is the amount of water, and once again, the data that we work. So at the top, it has all the water inside, and here it's the suction. So now just also to show there that, and this is important, if something dries out, it needs more energy than wetting up. Okay, so that's all that is basically showing. So if you wet up something, it's easier for it to mobilize. And when you dry it out, it's harder work. Okay, so that's why when something gets wet, that's all that's showing. It can start to actually move. Okay, so less energy is needed to wet something. Okay, next slide, please. Now so stop there. So that's normal fluid. So the viscosity for water is the same. And this comes in one of those references it matters. So this, if you can press another one. So some things, click please, when you move it, fluid, it actually plasticizes. So in other words, if you shake it, it gets thicker, like some greases and transformer fluids. Thank you very much. Okay, so that happens, but the one that now matters is that. This is what we work with, the tropic fluids that fluidizes with stress, like if you shake a bottle of tomato sauce. So another example is cement in those trucks that do that. It keeps it from solidifying by motion. Okay, so it keeps it in a liquid state. And that's also what happens with mud. So as soon as it starts moving faster. Okay, so it gains velocity. And in one of those references from the beginning, they say it behaves in a thixotropic way. Okay, because it does that, which means it liquefies, liquefaction. Okay, so that's what mud does. Makes sense? That's why I say this is overall more, so this is now Moore circles for those of you who know it. But it's that same viscosity strength, so in the laboratories they actually test wells, but now just the same there. So that's how they determine then the friction angle, the cohesion angle. So we do that, the engineers or the geologists calculate these. And that's then what it looks like different for swirls and clays. Okay, so just to recap. Okay, so just the pictures come later, but that now clay has low friction and high cohesion, which means that that can mobilize, and sand on the other hand, whoopsie, is high friction, low cohesion. Okay, so that happens. So cohesion pulls it together, can form mud. A sand doesn't, no mud. So that's once again what it looks like, clay and sand. Okay, so you can see that in the field, and that's the important thing, especially for the geologists, to in the field already know this. There's now also, we went through some of this, but yeah, now just go there. That you saw, basically recapping some, so we actually went through some of this. But now this, so there's the mud, there's the no mud, so a bit of recap, and that can form mud. Okay, so this is now a little example from the Rustenburg Gladstreet Gabbros. So that looks different, that's how we describe it in moisture content, but the grading curves look exactly the same. Okay, so once again, we shouldn't be misled. So these clays have clay, but that's the data that you get. Okay, is grading curves. So this is now from that reference. I just put this in here, not for boring, but so that you have actual references to say what the particle size distribution does. So they sift through a grain fries and do a hydrometer. So there's just some examples of, for your own reference, what it means. And another one, so another reference. Mobile sample, high fractions, just so that you have a record, but once again, we calculate that. Then iron or something can go in, that can change it, and any swirl, once again, will show under shear, so when you wet the swirl, it will fail, and slurries or mud. Okay, so this is now examples. And this is not all in mines, but once again, it shows you what happens when it wets up. Okay, so that's sands, and that's what happens when it fails. So in other words, sands cave in. So if you have backfill in the tailings or anything, it will happen. And if it can flow, become mud or whatever. But the point is that's an example of how sands fail in shear. Okay, swirls. So that's the consequence. This is now in a graveyard, but still that happens to your swirls. Percussion drilling you do. Many of you for data or different things. This is now an example of dolomite that I'm going to show you, but it's mobile. So that's what it looks like. We call that WAD. It's a swirl that's less dense than water. So it's WAD. So that's what it looks like. So that's mobile. So it is a mud. That goes down. It's not in a mine necessarily. Well, dolomite is that, but that's what it looks like. Okay, so that's what these natural muds look like. Okay, see, so that stuff. That's WAD. So that's a mud. And once again, just showing in your percussion drilling data, you can also see things. So sources, accumulation by combination of rocks or backfill. We went through that. And then that, but there's no examples. That, so once again, this we did. Backfill. Okay, so that's the engineering geology part. So I think we are repeating some stuff now. Oopsie daisy, and there. Okay. So now, there's the examples. So I took examples now that come from mineral suites. So this is now Marikana and Pretoria are next to each other. And Northern is to the north. So these are for platinum group elements. So basically, core stones are common. We'll get to an example where you have these enormous rocks inside that divert and concentrate water. Mud will be clay, depending on, and it differs. But once again, these are now the minerals that you mine from in those areas. Variable, proper field and lab testing. High water retention in those clays, so the water stays inside. But when it dries out, it desiccates or cracks. It's the only swirl that doesn't stay constant, and there's no examples of that. So that's at Marikana. It's highly expansive clays. Anyone know where Marikana is? It's north of Pretoria. There's Northern, so it's dry and more arid there. So the same rock weathering different, so less clay, so more likely to form a mud that can actually move. That's what it looks like in Claresworth if you look on the sides. Those are core stones, which means that all the water is forced in the rock around it. Okay, so there's just 3 examples now that I'm running through. Okay, so that's the soils that you form in the platinum mines. Okay. Next one, more that Witwatersrand, different soils. So you have clastic, you have shales, and you have the sandstone and everything, but mostly salty sands. Made materials, there's a lot of stuff that's made, filled and stuff, so that's not normal materials. That include tailings, that's also made ground, so that can move. Water through dewatering, there's a lot of deep mining, so in the gold mine, so that can now actually also dry out the soils from saturated, because water maintains the integrity of a soil. As soon as it dries out, it can consolidate. Okay. Water is affected through that then. AMD can change it, the chemistry and everything, and the soils act in corrosive then, that can also affect it. And then the basement granites under the quartzites, weather more. Okay, so in other words, there's weaker rock and soils below the Witwatersrand. So all of those soils can mobilize, and they're probably 45. So in other words, that's what happens there. So that is what you can see there. So that's polluted water or AMD. So in other words, that affects the water and the soils that move. So in other words, that's a new water with a new quality that now mobilizes the soil. So in other words, whatever mobilizes there as mud or anything has that quality. So as I said, this is about the soil properties more that I'm on today. And that's the tailings. So in other words, that can also mobilize. That example was there earlier, but water, gravity, and air can move that. And once again, when that mobilizes, it can also fall a mud or something that actually floods, mobilizes. So that material there is tailings. Everyone with me? Okay. So just examples from yours. So in other words, this is the stuff that you test with. And then the last one, Karoo Supergroup has a lot. Most of those that's mostly for coal and the proposed gas that will come. So as soon as you hydraulically fracture, that will happen. Burning, underground burning of coal can change it, which means that stuff can also mobilize. Foundations are heavy, so in other words, you have stations and everything on these, which will also mobilize clays, so the soil and stuff can move. Water quality may affect the soil, so these soils can be from any rock, so that's basically all the soils that you can get from there. And all of those can form different muds and stuff. So last example here is now what happens there, so that happens. So in other words, there, all of that mud or fine stuff can now flow down those tension cracks because the coal burns underground and forms sinkholes. So in other words, whatever fines are there, as soon as it wets up, it will flow down. Okay, mud. So that's what happens there, and then that's what happens with the water and stuff. So in other words, those soils also will fail. Okay. So the point just of all of this is that your data in the field and lab determine what can go into this. So every mine is different, every mineral is different, and the only thing here is that the water, the hydrogeology, and the engineering geology both play together, so that you can figure out if and how mud will be there, and if that will be. As I said, I'm not a mud flow specialist, but this is just some context. Okay, so there's the references. As I said, you can have it, the reading material, and that's the end. Thanks.
I think we're still good with time. Thank you very much. That was excellent, colleagues. I think we can give Matthias another round of applause. It felt like I'm back in class a little bit there, but that's good. That's what we need. That's what we need. Especially now with artificial intelligence, technology, engineers will forget, principles, the basics, the science behind the decisions we make, So I think that's good. I really appreciated that. We see so many AI slides. I'm guilty of that myself, So it's so good to see the proper theory and the science behind what we do. Colleagues, next I'm going to call Dr. Kim Morton, water strategist and mining hydrogeologist. She's joining us online. She's in London now doing work there. So we're really grateful she's made time for us. And I hope, Dr. Kim, can I ask if you can hear us? So what we'll do, we'll just project Dr. Kim's slides. Or Dr. Kim, we've said she will project herself so that she's able to move the slides herself. I think that might be more efficient. Are we good, online colleagues?
Hi, yes, good morning. I'm trying to share the slides with you.
Okay.
Just give me a second. Have they appeared?
Yeah, so I'll just check with our team here if we'll be able to project on screen so that everyone can see. Yeah.
Okay, I'm sharing.
Are you sharing now?
Yeah, so sharing.
Okay, Dr.
And
Kim,
I'm in
just please
presentation
put them on
mode.
slideshow, yeah.
Can you see the first slide?
Okay, I think that is the one, yes. With Minerals Council at the top. Yes, we can see Dr. Kim.
Yes,
You can
that's
go
it.
ahead. Yes, thanks.
Okay, thank you very, very much. It's wonderful to be here. I'm so sorry I'm not there in person, but I had commitments in London, but I'll be home soon. Unfortunately, not in time for the rugby, but I'll be home soon. So just a background who I am. I'm a consulting mining hydrologist. I've got over 45 years experience worldwide, and I've worked on over 300 mines. I started at WITS, and then I did my honours at King's College London, my master's in hydrogeology, University College London. My PhD is at Imperial College, and it was on Finch Mine, on deep block cave dewatering design. And then I realized early on, it's not enough to know your topic. You have to be able to explain it to the decision makers. So I then did an MBA at Imperial. I'm also a chartered geologist, registered in the UK. I'm a fellow, the Geological Society of the UK and South Africa and the Southern African Institute of Mining and Metallurgy, where I'm also a committee member. I'm an advisor to a Global Action on Tailings, the Global Minerals Professional Alliance, Pure Earth and Ramsar. I'm also an editor of the Mine Water Association Journal and the QJEG. So just to give you my background, I've had 45 years in mining and water, and part of that was 18 years working with De Beers, where we spent 3 years studying mud rushes, particularly after the early Vesselton problems. So this is a short talk, and we're going to look at incidents around the world, causes and factors behind mud rush and inrushes, building on what Professor Dippenaar and Mr. McKelly have been talking about and what William will be talking about later. The emphasis is that water is predictable. It's not an act of God. We can predict where the water is coming from, what it's traveling along, how much is going to arrive, and what the force will be that drives the mud into the mine. I'm going to emphasize the need for a guideline because there's a lot of work around the world and it hasn't been consolidated, and suggest a way forward. So as mentioned already, there are different types of mud rush. You will hear later on about the bow tie, where we discussed different types of mud rushes. And there's typically in the gold mines in southern Africa, there's an ore pass rush where the water builds up in the ore pass and then floods the mine after a specific event. But what I've mainly been concentrating on worldwide is the massive mud rushes from caving or from draw points. So if we're to look at the summary of fatalities from 1815, and Deshendra knows that we're very passionate about stopping these fatalities. They're not necessary. Since 1815, there's been over 1,420 people killed from mud and water inrushes. And the reason I'm combining them is often the mud and water are at the same time, or you'll have a water inrush that has mud as an associated flow, and then you also get mud. And of course, mud has to have some liquid in it to be able to move. And where these have happened all around the world, you can look at it. It's covering the entire planet: Australia, Burkina Faso, Canada, Chile, China, England, India, Mozambique, Namibia, Russia, Scotland, of course, South Africa, big mining industry, Ukraine, USA, Zambia, and of course, India. And the minerals covered, these have happened in anthracite mines, coal, copper, diamonds, gold, iron ore, platinum, potash, silver, zinc. And very sadly, the people who often get killed are the contractors, the ones working at the rock face, and they often have no voice. So I believe the Minerals Council is working very hard to protect those unheard people. So I'm going to talk of a couple of examples around the world, and we'll start off in Britain, Heaton Colliery. We'll look at Siberia, Mir, Kamakukula in DRC with a water problem, Mufalira in Zambia, Bultfontein closer to home in the Free State, Grasberg in Indonesia, and Mackay in the east of Australia. So let's just go back to 1815. This is not, mud rushes are not new, and water in rushes are not new. And this is close to where I was born in Britain, in the northeast of England. And Heaton Colliery, May the 3rd, 1815, 75 men and boys lost their lives. And you look at the cross-section, you'll see there that was basically an inrush from an aquifer that was tapped by the shaft. And all the water went into the shaft and killed those 75. That was the entire male population over the age of 9 for that village in 1815. And there's a monument you can see to the names of the dead. And it's very sad to read. But what happened in this is, I'm sure you're aware that mining safety advances by climbing on the coffins of the deceased. So although these very unhappy events happened, safety improves thereafter. And after Heaton Colliery disaster, the regulations came into force in Britain, where the earliest mining regulations were promulgated, to say that every mine had to have an escape way. So these poor men couldn't get out of the mine because there was only one shaft, and that shaft was damaged and flooded. But from then on, every mine has some escape way. So every death develops the safety of mining in the future. Another example, also close to home, in Zambia, Mufalira, 89 dead. And where that happened was, it's an interesting ore body in that it outcrops the surface. The open pit had been mined out, and then they were mining underground, which typically happens. And basically the tailings slid into the upper levels of the mine and then flooded the mine and with mud and water and killed 89 in 1970. Bultfontein mine, Howard Marsden's on the call here. He knows this mine better than anyone. And in May 2018, there were 5 buried in the mud there. So we've got from 1815 to the present day, we're still having these events. Mir diamond mine in Siberia. This is the open pit. It's a huge open pit. It's over 1 kilometer across, 500 meters deep. And the mine went into mining the deep deposit. This is the ore body here. And after they'd closed the open pit, they sunk shafts. They went in underground, they're mining underground, and water built up in the pit. And the bottom of the pit had been semi-sealed with the buildup of mud and what have you. And that broke through and unfortunately drowned 11 people underground with mud and water. So that's a very good example of do not have any water accumulating above a working area. Kamakukula, a very fantastic mine in the DRC. This mine went from nothing to first concentrate in 2 years, a very fast developing mine. This is going to be one of the wettest mines in the world. It's going to have to pump out about 6,000 litres per second, and it has already a problem with flooding. As we know, the DRC Zambia copper belt is a very wet mining area. Grasberg mine, another project I've worked on in, I've got to get rid of that thing. In September 2025, they had a serious mud rush. This is the open pit in plan view. This mine is 4 kilometers above sea level. They have equatorial glaciers. Basically, they first of all took off the top of a mountain for the ore. They then developed this very large open pit, and now they have several block caves underneath the open pit. And sadly, in September, again, mud entered from the bottom of the open pit into the block cave and killed 7. And if you look into the pit here, you can see that white area there. That is debris that's collapsed into the bottom of the pit from the old open pit. And water has been allowed to accumulate in that because the material in the bottom of the pit becomes a sponge. And then that water can build up and create mud rushes into the underground workings. And one of the reasons I'm talking about Grasberg is they use a method of mining called block caving. Block caving is a very clever method of mining. It was developed in Zimbabwe by a very clever man called Dennis Loubser. And what happens here is gravity is used to drive the broken rock into an extraction level. So basically, the bottom of the mine is developed as a chessboard. This can be a kilometer or so below surface. And that chessboard has intersections where draw points are developed, very strongly supported. And then the broken rock above trickles into these draw points and is then taken away by LHCs or others to the shaft and then to the process plant. Now, of course, because it's very clever using gravity to drive the ore into these draw points, gravity also means that all the water in the area will move into that area. So I'm going to talk now about how it's possible to divert that water away from these draw points. So looking again at Grasberg, there's the open pit, there's the block cave. If we look at it in some plan view, these dots are all, there's some 200 draw points they have operating here. And this area here, the PB1 Central, is where this latest mud rush happened. So it's very important to look at not only in cross-section at the design of the mine and the block cave, but also the planning of how this is going to be extracted. And in the De Beers experience, we always plan to shuffle the rock down evenly and not create a gradient, because if you create a gradient, that can also attract water to the lowest point. So what is really important is divert the water away from your mining area. So again, I've shown you, this is a blow up of Grasberg, the build up of rock at the bottom. And of course, best practice for an open pit is before you close the open pit, you basically put in catchment dams and you collect as much water as possible to minimize the amount of water going into the bottom of the open pit. And of course, this being up a mountain, it's very straightforward to divert that water and drain it out the side of the mountain using techniques going back 2,000 years to Roman times. And then the reason I'm talking about mud and water is Burkina Faso. There were 8 dead there, where water came in the mine entrance and flooded right down to 800 meters and basically drowned 8 people there. So it's very important we look at mud and water together, because often the contributing factors are the same. So they need to be tackled together. And mud rush is where mud enters the mine and engulfs people and machinery. It always needs water to drive it. That is the head. That is the force. That is the potential and kinetic energy which creates these mud and floods. And then a flood is an inrush where water enters from surface, either from the surface itself or underground pockets or neighboring mines. And so water and mud need to be tackled together. So water is a very important part of the prediction of mud and water rushes, and also a force that you can divert easily. Water can be controlled. And the way we know that is water is part of this hydrological cycle. So everyone knows that the snow will fall as precipitation. It'll move to the lowest point, eventually to the sea. You've got evaporation returning the water from your natural water bodies and also your tailings and discard plants. And then when you put in a mine, either an open pit or an underground mine, there's the underground workings here, you start diverting that water. So you create what's known as a cone of drawdown. Can you see that cone shape is the water table where water is being pumped out of the underground workings? What's really significant about this slide is this shape of the groundwater flow. Groundwater doesn't just flow vertically or horizontally. It flows in a U shape towards your pumping node, there's a pumping borehole there, or towards the underground shaft. And so it's absolutely vital to understand the direction of flow. And so you've got your surface water coming in, you've got your groundwater coming in. You need to know where the water's coming from, how it's traveling, what it's traveling along, and what it's stored in. Once you know those, it's very straightforward to start diverting that water away from the working area. So my point is that water is measurable and predictable. This is an example from Australia for a coal mine called Hale Creek. And what we know from modern satellite interpretation is that the moisture content of the atmosphere can be predicted. So if you look at this map of Australia, you'll see there's a big cyclone coming in from the northeast towards Hale Creek. That's showing where Hale Creek is. So we can use science to say how much water is coming towards the mine in the atmosphere. Oops. And if we look into the pit, this is a very long pit. It's about 5 kilometers long. It's almost a kilometer deep. And the challenge we had on this project was we had very big equipment that sat at the bottom of the pit. And it can take 2 days for that to leave the bottom of the pit. So it's very important the mine knows if the rainfall event coming is going to drown this equipment, in which case they have to start 2 days in advance to start getting it out of the way of the flooding. And the way we did that is we put in a monitoring network. So there's the pit in plan view. That's about 5 k's and that's about 1 kilometer across. These red points are all boreholes that are measuring the amount of water in the aquifers around the pit. And we've also got monitoring points in the stormwater dams, the catchment dams around the pit. So with those, we can measure how much water can the ground absorb before the pit starts to flood? How much water can the stormwater catchments take before they overspill or seep into the mine itself? So in this example, we're showing a cyclone coming in. Prediction from the NASA moisture content predictors show there's about 80 millimeters going to fall in about 12 hours. So you can calculate the volume of water coming in. You can calculate the ready available space. And depending on if that space is enough to absorb this water, you can put in a red, an amber, or a green on a dashboard that can be looked at by everyone on the mine. So that would enable them to make the decision, do they start moving equipment out of the mine or can they leave it there? And that can save millions in production. So that's an example of surface flow inrush that can be predicted. If we look at underground mines in more detail, this is an open pit, and again, we've got the ore body below here, and we've got the block cave layout. We can see from this how the water flows from surface, accumulates in the groundwater, and it actually then moves into the caved area. So your low point is always your mining area. So the water always moves from high to low pressure. So you're able to predict where the flow lines will be, and you can predict what the table is, and you can also then say what water table is acceptable to operate in this mine. And logically, given that water always flows from high to low pressure, if you keep that water table below your extraction level, there cannot be water inflows that's significant enough to kill people, and there cannot be mud rushes. So this is your target. Keep the water level below the extraction level. And then this is a complex mine, and you've got the open pit, you've got an underground drainage gallery, and you've got a sort of staggered water table. We've got a drainage tunnel here and a drainage tunnel there. But the objective of this type of diagram is to be able to put in drain holes and drainage galleries that keep the water table below your undercut and extraction level. In other words, protect the people working underground. And of course, this is schematic. And reality, it's a bit more complicated than that. But this is what you're trying to achieve. If you keep the pressure of water below your working area, there cannot be mud or water inflows. So the fight against mud and water inrushes means you actually have to have a good dewatering strategy. And that's what I've worked, as I said, over 40 years on dewatering design. An accurate dewatering requires a quantitative understanding of the sources of water. In other words, what's coming in on surface, what's coming in underground. The flow paths, what is the water following? And a typical conduit would be a fault or a bedding plane or even haulages, any open space in the rock that allows water to flow from high to low pressure. And they can be natural and man-made. So critical part of a dewatering design is creating a hydrostructural model. And in sub-Saharan Africa, particularly southern Africa, we know that north-south structures are typically tensional, and they will be good conduits to collect water in. And we know the east-west structures are typically compressional. We all know the Cape's being pushed up by tectonic forces, and we know that KwaZulu-Natal is trying to break away from South Africa, not just politically, but also physically, because the East African Rift is attached to the Natal monocline as well. So we know that KwaZulu-Natal, we've got tensional forces there. So north-south structures will be carrying water. And then, of course, storage. And that can be man-made storage. In other words, are there impoundments above the mine? And you will not believe how many mines I've worked on where they build a holding dam above a caving area. But serious, the surface guys often don't talk to the underground guys. So this is a simple area to sort out. And then underground storage, as mines get deeper and older areas are closed off, it's vital that draining systems are put in so that water cannot build underground. And then pressures and pressure distribution, that can be measured very easily with vibrating wire piezometers and open boreholes. You can measure pressures and pressure distribution. So to understand the hydrogeology and the dewatering design for a mine, this is a model flow diagram that we developed at De Beers. Alan Guest basically designed this. And over 18 years, we said to have a thorough understanding of how the water and the geotechnical and the mining all fit together, you need to have a geological model of the ore and country rock. And often a good mine will have an ore body model, but often there's no country rock model. And where's most of the water coming in from? It's coming in through the country rock. So it's vital the country rock model is as good as the ore body model. And often that means two different types of geologists. Ore body geologists are not necessarily good structural geologists. And then that information can feed into a structural model, which then feeds into a hydrogeological model, which then feeds into a geotechnical model, a rock mass model, and results in the mine design model. So this is the flow diagram, and you can see there's also feedback loops here. So the geotech feeds back into the hydrogeology feeds back into the structural model, and that also feeds back into your geological models. And often, particularly Rio and BHP have got a good handle on this by having a shared database where everyone's pulling information from the same rainfall data, the flow rate data, the geology data, water levels, and the mine plan. Now, this is a very complicated slide, but it shows the flow to achieve a mine dewatering design. So you start off identifying the problem, you collect site data, you develop a conceptual model. And can you see there's feedback loops in this as well? You're always querying what your conceptual model is. You identify options for dewatering, you build a numerical model, you calibrate the model to site data, you run sensitivity analyses, you make predictive simulations, you set dewatering targets. This is absolutely critical. I've worked on many mines where they believe by pumping, say 30,000 cubic meters a day, they have a dewatering system. But pumping is not the objective. The objective is to lower the water level below a target level. And a classic was in Australia. I was called to help the mine dewater a pit, and the pit was flooded. It had been flooded for 3 weeks. And basically, I said, well, what are the engineers' KPIs? Because this was not a complicated pit. And the engineers were given bonuses on how much water they pumped out. But what was the objective? The objective wasn't to pump water. It was to keep the water level 1 bench below pit bottom. So we put in some monitoring holes in the pit bottom. We changed the KPIs so the engineers got bonuses on keeping the water level below the pit bottom. And lo and behold, we had a dry pit. So remember the law of unintended consequences. If you set a pumping rate for a mine, that will not dewater your mine. But once you've got the dewatering target, you can then modify and implement a dewatering design. You can observe the success and adjust design and targets, taking into account the human factor. You update the model, and then you can see here there's constant loops in this process. So for dewatering success, the essentials are cut-off recharge. So that would be a good stormwater design. Keep as much water away that's easy on surface away from your mining area. Exploit permeability. What that means is go underground with your hydrogeological model and see where it's easy to pick up water and divert it. A classic in the Congo is there's usually a bedding plane below the ore body, which is permeable. So if you suck the water out of that away from the mining area, it will dewater the mining area. Again, you have to start early. It can take up to 2 years to move the water away from a mining area. Set water level targets and monitor levels and flows. So to be more specific about mud rushes, as mentioned earlier, there are 4 factors. The first is you've got to have mud for mud, and that's slippery rocks in layman's terms, or low friction material if you want to be more scientific. The driving head of water. So this head is the force. If you remove the force, there is no problem. Obviously an outlet, a draw point, or an opening And then there's always a trigger. And typical triggers could be seismic, man-made, or an earthquake. And then an important trigger is increase in head. So you could have the water targets you want, but if an event happens in that there's a breach of some water somewhere and the head increases quickly, that can be a trigger that sets off a mud rush. And then on the geotechnical and mining side, overdraw can create an unstable gradient and attract more water to the draw points, and then your blasting pattern, which is beyond my area of expertise. So this goes back to the document produced by Simrak in 2000. And again, this has been the sort of industry standard for 26 years, where you've got a muck pile head driving force. It's missing the water factor here. It's really critical we add water as a major driver into this. And of course, these are very relevant. You've got a large rock arch occurring, a void's created, the arch inhibits downward movement. Under the head of the muck pile, which is full of water, the drawing starts the rock arch collapse, the draw column compacts, the mud pockets discharge, and as mud is forced along the drift, you can have compression creating an air blast as well. So this is a great start to build on 26 years later. And as shown earlier by Matthijs, Jarek Jakobek, who I saw at the caving conference earlier last month, he basically looked at an assessment process. And of course, what's important is the source of water is now being added into the mix. So this is important, the quantities and distribution of water. And then that would add to the mud forming potential, the mud rush risk analysis, and going into the controls. So what we're moving towards now, 26 years later, is looking at causes, not symptoms. So if we were to update the 26 model, we'd have this sort of diagram, where we've had the presence of the mud-forming materials, the head of water, a phreatic surface which is above the maximum level, your discharge points and your triggers. So the critical difference 26 years later is adding this head of water, the force that's actually going to drive the event. And again, I apologize for the complexity of the slide, but basically we're looking at the elements and how we can control them. Remember, we don't want to look at symptoms. We don't need to measure the water coming out of individual draw points. We need to look at the causes of the water and mud reaching a draw point. So we've got the presence of mud-forming materials. What can we do to control them? We can reduce the muck pile. Do not allow the mud to build up in the pit bottom. You can reduce the pit slope failure by having a better closure plan for the pit before it's actually closed. You can adapt blasting. You can reduce contact time with water, and that refers back to Professor Dippenar's comments on the creation of mud. If the water is kept away from the material as long as possible, then the proportion of materials turning to mud is reduced. Look at the head of water. You can keep the phreatic surface below the extraction level. You can maintain a detailed water balance. This is critical. If you can, in your mind, make sure that you're always pumping out more water from the mine that is going into it, you cannot have a buildup of water. If you cannot have a buildup of water, you cannot have a buildup of mud. You can monitor your head distribution in 3 dimensions using vibrating wire piezometers and dashboards. You can measure water ingress at the draw points. You can improve mine design to divert water. We had very great success at Cullinan Mine outside Pretoria, where there was a fault draining the BB1 East Block Cave. And that meant if we pumped that fault further along on, I think it was about 680 level, we could suck the water away from the mining area and keep that dry to protect the people and enable a more safe block cave. And of course, ensure very good drainage of closed areas. Then discharge points. You need best practice geotechnical design. Map the water ingress. Spot the areas where water's coming in. Particularly on a kimberlite mine, you'll have areas that water flows along particular kimberlite intrusions. And that, again, those permeable areas can be used to suck water away. And then have an early warning system of water pressure buildup. So not only do you measure what the water levels are, you measure the rate at which that changes. And then looking at the triggers, you can have better management of the draw, better quake prediction, and of course, accurate stormwater diversion. Drain your upper levels, control your pit drainage, and show water out and water in. So this is very broad brushstrokes. These are the elements we need to control. And again, I've shown you the conceptualization. This is a typical mine and how you need to divert that water away. So we now have a new strategy building on the 2000 work. We monitor the cause, not the symptom. We prevent, not mitigate. And we develop an international guideline. So causes of water and mud rushes can be monitored, predicted, and prevented. So monitoring would be real-time groundwater level monitoring, piezometers and observation boreholes, flow measurements and pressure monitoring, water balance audits. Prediction will be rainfall topography modelling, groundwater level modelling, risk mapping of water-bearing structures. Never forget the country rock geology. Early warning thresholds and trigger levels. Establish those and avoid them. So prevention, controlled integrated dewatering programs, measurement of head and flow lines, use of drainage drives and pressure relief systems, use of satellite imagery and early warning of water coming into the catchment, early warning dashboards for trigger levels, and the speed at which water is moving towards a trigger level. Operational risk management procedures, which I'm sure William will talk about later, and the bow tie. Integration of water management. So the strategy now, which we're discussing with Minerals Council, is the first task. Let's establish a comprehensive list of all occurrences, obtain the regulations worldwide on water inrush and mud rush prevention, evaluate the causes of historic mud rush and categorize them. What do we need to prevent? Task 2, draw up guidelines to monitor, predict, and prevent. We don't want to mitigate, we want to prevent them. Water inrushes and mud inrushes for each mine type and climate type. And then task 3, distribute the guidelines and work with stakeholders to ensure implementation. So the accurate management of the water drainage for a whole mine needs regularly updated water balance that ensures water out is always more than water in. Annually reviewed detailed hydrological conceptual models based on detailed hydrostructural model. This is absolutely critical. Understand the matrix around your mine and how the water is reaching those draw points. Seasonally update and accurate surface water control, prevent water entering the pit and underground mine through open holes and the zone of relaxation. That's the break zone around any excavation. And then detailed proactive dewatering designs for each sector of the mine. You cannot have a bulk dewatering design. You have to look at each sector, its geology and hydrogeology. Use dewatering galleries and large diameter drains or pumping wells to keep the phreatic surface below the extraction level and divert water. It's always better to divert than try and hold water back. Think of King Canute trying to hold the tide back. You cannot hold water back. You need to divert it and work with it. And then annually updated monitoring networks, heads and volumes that report on the location of the phreatic surface in 3D. So the key takeaways for the water balance for the mine in entirety and different sectors, ensure the water out is more than the water in. Divert the water from the workings and maintain head below extraction level. Monitor head distribution around the cave and create a gradient away from the workings. So don't let mud or water surprise you. Drown the risk, not your mine. If we measure, we can control and then prevent. Thank you very much.
Thank you very much, Dr. Kim. That was excellent. And I love how we've moved from, the science, the basics, underlying theory to more application and practice that we can use to fight this war. So I think that was a nice flow, Dr. Kim. Thank you very much, and Matthias, actually, for that nice link. Dr. Kim, you'll be here for the panel discussion.
Yes, of course. I've been on since early this morning. I'm with you.
Awesome. Oh, that's good. That's good. Colleagues, I hope we've taken notes, have some questions, so that we can be more interactive, later on when we have that session on the panel. So we are 12 minutes past 10. I'd like to ask we take a break for now as per program, and we then reconvene at 10:30. Thanks, colleagues. Let's take a break, and we'll continue at 10:30. Thanks. And it will be Mr. William Yogan, because, as Dushendra said, we won't be having Manas today. Thanks, colleagues. William, it's fun, no? All right, thanks. All right, perfect, thanks. Sorry, the pointer is... Colleagues, it's 10:31. We're getting some interference. Can I confirm if the presentation will be flighted? And just to remind you again, colleagues, an apology from Mr. Manas Fourie. Dushen did share with us that he was really keen on sharing from his side, but unfortunately he could not attend. But I'm sure in our other sessions that we'll have, it will be really interesting to hear from his perspective as well with the important work they do, from MRS. So are the colleagues from MRS here, right? Oh yeah, no, thank you for being with us. So we'll just then pass the presentation from Manas, but it did pass his regards to the team for today. Are we able to flat the presentation, colleagues? Is it on now? Yes, so I'll just ask then our next presenter for today, Mr. William, to please come on stage from SRK Consulting. You'll be presenting on mud rushes and end rushes, lessons from investigations, and the evolution of risk management. Thank you, colleagues. Over to you.
Thank you very much. Yeah. Let's see how this... can you try and play the video from there? I'm not quite sure how to do it on here. Yeah. So this is a mud rush at Cullinan Diamond Mine. It's quite a famous video. It's been shown all over the world. And it's a good example of this challenge that we have to face. So just, my name's William Joch, and I'm a mining engineer. So I've started working on deep gold mines. When I joined SRK, one of the first jobs that I did was work on a research project on mud rushes, and that's how I got involved. So the SIMRAC project that's been referred to, I was part of that project. The leader of that project was Richard Butcher. I'll mention that a little bit during the presentation. And my colleague is Gerard Keita. He's online. He's a civil geotechnical engineer, and he's worked on quite a lot of caving mines and had to deal with mud rushes as well. So we've jointly prepared this presentation. And just, I guess I'm not a specialist in hydrogeology, so I'm going to rely very much on the work that Kim has presented already, and then also in terms of the soil mechanics. Thanks, Matthijs, for going through some of that theory. So I'm going to try and focus on the practical aspects, the mining, and give you a bit of an overall picture. So this is my contents. This is what I'll try and cover. I might overrun a little bit, but we've got an extra slot. I hope it's interesting because they're caving studies. There's not much theory in this. It should hopefully be very practical, and hopefully you'll find it interesting and useful. Yeah. So I'm going to start just talking a list, give you a list of major mud rushes. Sorry, the table is very busy, and you won't, you might not be able to read it at the back, but I'll just walk you through it. So what I did was I just tried to compile a list of some of the most significant mud rushes that have occurred in mines, starting at the top there is the Grasberg one, which Kim mentioned, which is, I've sorted these actually by volume, just to give a sense of the severity of the mud rush and so on. And at the top is Grasberg with 800,000, and that I don't have a lot of information on Grasberg itself. I haven't worked there. It wasn't presented at Caving 2026. But the official one is that there was external wet material from the pit that entered the mine through an unrecognized pathway. And that flowed through the extraction level, through a panel drift, through vent raisers, wall passes, and drainage ways all the way down to the service level. So that as you can see, was quite a catastrophic mud rush. The statement suggests that there were the unrecognized pathway, how that material got into the mine suggests that it was something that they hadn't anticipated. So Mufulera is the next biggest one, which Kim also mentioned. I do have a slide on that, and I'll talk to that very briefly. The next largest one is Mir, which was in Russia. I'll quickly talk about it. I did try to get permission to talk about Mir. I was part of an investigation team immediately following that accident, in which 8 people lost their lives. So it was quite a tragic thing, a tragic accident. There were so our team actually comprised. We had 2 rock engineers, 1 Russian, 1 international. I was the international one, and 2 hydrogeologists, 1 from UK and 1 with international experience, and 1 from Russia. And then we had 2 professional Russian translators to help us work through the mountain of documentation that we received in Russian as part of that review. And I think and we also had eyewitness accounts, which was quite, I guess, quite raw, because it was literally a week after the incident occurred. And you can imagine they've lost their friends, and they've had, at some point they had to stop the rescue operation and recovery operation because of because the pit was filling up with water again, and it was unsafe to continue working there. So, looking at, I'll just give you a brief overview. I did request permission to present some of the information. I do have some nice slides, but I did not receive permission in time to present it. But basically, they designed, it's quite an unusual, it's a kimberlite pipe, but unlike we've mined many kimberlite pipes in South Africa, but unlike in South Africa, they didn't go for a caving method, and part of this is because of the country rock. So above the open pit, for the open pit, the country rock was predominantly dolomite. There's a dolerite sill at the crown pillar level, and there was the country rock was halite, which is salt in the side. So they had gone through quite a thought process and going through probably the most expensive mining method, which is drift and fill. So they had a crown pillar and then sill pillars between main levels, and then each slice they were mining drift and fill. Now, what actually happened there is they did design a drainage system in the pit, which was quite a comprehensive design. But I guess what went wrong is they didn't have a contingency plan for when the adits in the side of the pit silted up, and they were unable to once they blocked up, they were unable to manage the drainage. And they tried to drain it from underneath, but before they succeeded, they had a chimney failure at the contact. So the contacts of kimberlite pipes are intensely jointed and fractured, and they often have clay minerals. In this case, it was talc and serpentinite which would have come from the kimberlite, and it also had some salt, some halite along the contact. And they developed an excavation within the contact zone, which is which is generally not advisable. Try and avoid that at all costs. And what happened is there was water seeping through from the pit along the contact, and about 2 weeks before the incident, they started developing a chimney failure in that excavation, which they attempted to backfill, but it was not successful. And then, I'm sorry I can't show you the slides because that would have got that message across a lot more clearly. I think I will get permission and I will be able to use those slides in future. So I've then slotted Rovik in next. I don't have actually a figure for the volume, but I've just kind of guessed where it would slot in. So that was certainly before I started working that occurred. 1996 I would have been working then. And there's quite a lot of detail on that report. That was also a crown pillar failure. They were using chamberage and shrinkage stoping underneath. And then a Keep copper mine was the next biggest. That occurred in the 80s. I don't have a fixed date for that, but it was attributed to liquefaction of the backfill in the large stope and a bulkhead failure. I'm going to talk about prevention of backfill mud rushes in general, rather than specifically on that particular case. The Bultfontein case, Kim introduced it. Howard Marsden, who will be speaking after me, he was operating on the mine, and we were asked to review the incident. So we were involved in the review after the accident, and I had a team, a civil geotechnical engineer and a hydrogeologist working with me on that review. But I'll talk about that a little bit more. So another interesting one is Argyll, Australia, which I picked up from a paper that was presented in Caving 2022, where they had quite a significant mud rush, 18,000 cubic meters, and they had a top. I do have some slides for that. And the last one I have on this list is the Toyspan, which Howard is going to talk about in the next presentation. So the information I've got in this presentation actually comes from information that Howard provided. It comes from his presentation. So I'm not going to talk specifically about the Toyspan. I have not investigated it. I'll quickly just go through backfill mud rushes. So this is where I started my career, working in narrow tabular stopes. And this just shows some examples. These pictures actually come from South Deep. So I'll just quickly, it has a lot to do with the management of this risk has to do with the paddock construction, and then your quality of your backfill, your selection of the type of fill that you use, and monitoring of the backfill, and then also managing the exposure of people, so restricting access during filling, and that's usually how to manage it. While I was at South Deep, we did have a fatal accident, which was associated with a stope that had an unusually steep dip. So so the head was higher than usual, and the bulkhead construction was insufficient to cater for that. So that resulted in a significant change in the standard, and to try and improve that. This is a very practical construction. I've just listed some of the materials that are used. You're certainly not going to do a mathematical calculation to design this bulkhead. You really need to test it. You need to test it practically under control conditions and make sure that it's working. And then long hole open stoping. So I've drawn most of these pictures, or all except for one, from the two very good books by the Australian Centre for Geomechanics. The first was published in 2008, and second one in 2025, and that highlights quite a lot of the information that you need to design long hole open stope safely. So yeah, the latest one, the 2025, is quite a considerable update on the earlier one, and it's certainly a very good book. I'm not going to spend too much time on this, but again, it comes down to the choice of backfill, design of the backfill. And the bulkhead design and construction is quite critical. There are shotcrete bulkheads, arch shotcrete bulkheads are used quite extensively, but in other places they used waste rock berms and or full fences comprising geotextile fabrics. In the case of these lighter barricades, you have to fill much slower, you have to have more controls on your drainage, so your turnaround time on your stopes is quite a lot lower than if you have a designed bulkhead. But there is a lot of technology available to manage this. Okay, so this is courtesy of Gerard, so it's not just mud that flows, so sand actually does flow without any water. So this example is Kagu was essentially a crown pillar failure where the crown pillar comprised sand, and when the failure occurred, there was dust blown out and part of the level and was filled with sand. Okay, and that just shows you a level plan. They were using sub-level caving, and without going into too much detail, I think the main issue is that the original design relied on using an ore blanket to protect you from the sand, and due to overdraw, that ore blanket was essentially removed, and the sand went into the workings. Sorry, I'll go back. I'll quickly cover the Mufulera mine disaster. So I managed to find quite a nice picture that shows the incident. So they were that came out of the Clark and Jakobek paper in 2026. So basically, they were using caving methods underneath the tailings dam. So it was a combination. If you go through the report, you'll see that they used block caving methods in the flatter areas and sub-level caving methods where the dip was a little bit steeper. And that sort of schematic diagram gives you an indication of the underground layout and section with the tailings dam above it. And basically, as you would expect in a sub-level cave, the hanging wall collapsed, which created a pathway for the tailings to rush through into the underground workings. And so, and this was probably the most dramatic and tragic, where it basically the mud flowed in apparently at 500 cubic meters per second, and it flooded the mine within 15 minutes. Yeah, it was, and there were 89 fatalities, so people trapped underground. So it was quite extremely tragic incident, but it just highlights the importance of a robust, stable mine design as opposed to a caving mine design underneath the tailings dam. So in general, I just want to get this picture I borrowed from my colleague Jarek Jakubek. Apologies, the resolution's not so good, I enlarged it. But it shows the development of a block cave from the initial undercut through then propagating as you draw ore from underneath and then break through to surface. And then what I've drawn in here is you get So it's sometimes the ore and the immediate host rock does contain mud-forming materials, so rocks that break down into silts and clays. But we generally tend to get more of that kind of material near surface, just because of the weathering or transported soils and so on. And you can get slope failures and mudslides and various things, and you get comminution and weathering of different types of ores. Then groundwater, so your groundwater risk also changes with time. So initially you would have you might have an aquifer some distance above the cave, and then your connectivity is through faults. Until you eventually break through into that aquifer, and then you break through to surface, and that risk profile changes with time as a result of that. And then, so rainfall and precipitation has played a significant role in quite a number of the mud rushes that I've reviewed. So. This, I just want to show you how the topography, and in this case, if you have an open pit on surface, that can accelerate some of the challenges that you experience. In this case, this comes from New Afton, this cartoon of the cave. So they've got a completed cave which broke through to surface, and then they're extending down and extracting the B3 cave. They're actually extracting another cave down below at the moment. So you've got to consider, so initially that B3 cave, for example, would have a lower risk until it connects into the old cave. So the geometry of the cave at the different stages in the life of the project also affects the risk quite significantly. Another big factor in terms of caving at mining is draw control. So I borrowed this picture from Dennis Loebsch's, on the left, from Dennis Loebsch's handbook on caving. On the left-hand side, you see what we refer to as isolated draw. So when you're drawing primarily from one drill point and not drawing evenly, even draw creates interactive draw, and that means that your muck pile moves down all in one go. Whereas if you have isolated draw, you create these rat holes in the muck pile. So you create voids within the muck pile, and that creates potential flow paths for mud. On the right-hand side, you can see rat holes in a subsidence crater. So I've given you the reference for that paper as well, which shows rat holes that extend to the surface of the muck pile. So obviously, if you have high rainfall and runoff from the slopes, that's going to go straight into those rat holes that have developed. So this is the 2000 work, the SIMRAC project, which Richard Butcher led the study, and so most of the thinking actually comes from Richard Butcher, who spent several years working on the Kimberley mines and having to actively deal with mud rushes over the years. And so this picture comes from there. So I'll just step through it. So you've got, number one, he talks about the shale weathering from the slopes, and it falls on top of the muck pile. You'll see in this picture you've got more competent rocks which don't create mud-forming materials on the left, but they do create boulders which also form part of the muck pile. But you often have this fine layer of silts and clays on top of the muck pile. That's number two. And then number three, that shell gets drawn into the waste cap, and then you also get rainwater entering. And number four, the void. So those voids are, I mean, we have air in the cave, believe it or not. We have great big voids with air gaps in them, and which create preferential flow paths. So that comminuted shale and kimberlite content, they mix within that, and the rainwater mix with the mud to form pockets, and then that eventually it comes down the muck pile and gets into your draw points. So mud pockets are created. So I think one of the points I want to make is this: the muck pile is, particularly if we've got quite a large muck pile, it's not homogeneous at all. It's got a mixture of rocks. It's got rocks. It's got mud. It's got water. It's got air. It's got all sorts of different materials in it, which does make it quite challenging to understand what is going on in the muck pile. I've just drawn pit lakes on top of the muck pile. I've added that in. Sorry, I'll just go in. So number 8 is a pit lake. So because you've got this fine material on top, it forms a pit lake. So if you have coarse material on the top, the water will run straight into the muck pile. It'll run directly into the muck pile. But if you've got that fine silt material, it can form an aquiclude, which enables a pit lake to form. And it could just be basically sitting on top of coarser rocks. So because of the inhomogeneity of that muck pile. And then, and these rat holes obviously play a significant role in the muck pile. So I think one of the important things I want to get across, and thanks to Matthijs for explaining Soil Mechanics 101 to you a little bit earlier, but that moisture content of the mud is changing continuously. So it increases when it comes into contact with water that is filtering through the muck pile, and it decreases through drainage and evaporation over time. And then disturbances such as draw, agitation, seismicity, blasting, they enable mixing and liquefaction and formation of mud. And those properties vary depending on the moisture content of the material. So practically they can act as an aquiclude, so they can act as a barrier to hold back water. They can create arching in the muck pile, which creates voids underneath it. And then in the draw points, we see very hard plastic mud sometimes, which is extremely difficult to handle. It's very, very, and we refer to mud pushers, which is slow plastic flow, so that's with a relatively low moisture content. And so sometimes it just squeezes slowly out of the draw point. You know, could be moving at walking speed, or it could we're moving so slowly you have to measure it in days. And a mud rush occurs when you've got a much higher moisture content, obviously, and you need gravity. You need to be able to, it flows downhill, it needs to have significant moisture in it, and then it builds up momentum, as Matthijs explained, as it starts moving. And it can move extremely rapidly. So this is a nice picture I just got from a El Teniente, so from one of the papers, which just shows their experience of water filtering through the muck pile and creating mud. So you've got the coarser material, voids are created in the muck pile through the drawing process and movement in the muck pile, and that enables the water to flow down. So the surface water accumulation above the cave footprint is quite is an important thing to consider and to monitor. This is another picture from El Teniente, which also shows nicely I hope you can see little blue trains and brown going through so mud and water flowing through much coarser material. So that is, and then it's reporting in the draw point. So these mud rushes didn't make that list that I mentioned there, but they nevertheless were significant, and some of them caused fatalities. So I'll spend a little bit of time on the Bultfontein mud rush, and with just to I'll try and go through this rather complex mud rush. It was so the Bultfontein mine had not experienced major mud rushes until this particular occasion, and then they experienced the biggest mud rush, which was 38,000 cubic meters. And it has been published, so it was published in Massman 2024, so this information is available. And it's it filled the 3 bottom levels, and this is a very old mine. So they started mining in the 1880s. If you've been to the Kimberley Hole and you've seen how this was started at roughly the same time with the same sort of mining methods, starting off with those primitive open pit mining methods and then going into chambering. There's a nice summary that Howard presented in that particular paper. They transferred into chambering and other methods as they went underground. And then they started with block caves. I think it was somewhere around 1950 odd where they started with block caves. And I've shown, you'll see block cave repeated. There's a number of lifts on that block cave. So where the mud rush occurred at the bottom of the muck pile, 845 was the extraction level for the slusher block cave that they were mining, and then there are two sub-levels that were developed below that. So the 865 was very much in production at the time, and the 885 had not started. So one of the issues in a sub-level cave, because you're retreating, so you load from one ring at a time and you retreat towards the contact of the pipe. So the 885 level was not ready yet. So they were drawing from the rim and trying to extract some old kimberlite from that 845 cave, trying to get that out. But that carried on for quite some time, and the volume of ore that was drawn out from that contact was significant. And this picture indicates a rat hole, essentially a cavity that could potentially have been created within the muck pile. And I say potentially because we can't see in the muck pile, we can't tell what is in there. So one theory is that the rat hole propagated all the way to the pit bottom where there was a lake, a pit lake. But I suppose it could have also followed, there could have been connections with old rat holes in the muck pile and various other things that are complex. We also know that because we've seen that they've observed from time to time that water comes out of the muck pile, water and mud comes out of the muck pile at different points. So there is water and mud in the muck pile. So I'd say of the people that reviewed us, we agree on most aspects, but that reviewed this incident. But because we can't actually see into this muck pile, we cannot conclusively say exactly what happened. I'm of the opinion that it did, in fact, connect to the water in the pit bottom. I'll go back to that. So this is, so to actually see inside the pit, you've got to do a flyover. They're being done far more frequently these days. So a few days before the mud rush, there was a large accumulation of water above the muck pile, and then the day after the event, they did a survey again, and that pit lake had emptied. The estimated volume of that was actually significantly larger than the amount of mud that went into the excavations. So some of that must have been left inside, must have remained inside the muck pile. This is an Argyle mud rush. So this I've got from this paper that I haven't put in a reference for. So I thought I had the reference in here, but this was presented in Caving 2022. So this occurred on the 4th of February 2020. And if you look at the surface with the production level indicated underneath, you can see old rat holes in the muck pile that they'd mapped out. And they had a 18,000 cubic meters of wet material from the draw points flowed into the cave, and you can see that in the picture here. So that took up about a third of the extraction, filled up with about a third of the extraction level, covering an area of more than 5,000 meters squared. And this was triggered by a significant rainfall event of 161 millimeters over 4 hours, which was above their 100-year flood situation. And they postulate that what happened is that water flowed directly through those chimneys, accumulated in the muck pile, and the hang-ups that were in the draw points would have held it for some time, and then that eventually failed. So they had a sudden collapse of those hang-ups because they were not actively drawing. And part of the reason for that is because they had activated a top because of that unusual rainfall event. And I think what's interesting, if you care, compare it with the previous case with Bultfontein. The mud rush occurred 4 hours after they activated the top, so 4 hours after they realized that there was quite a significant event. Whereas that pit lake at Bultfontein was there for several months, and so it is, and they at Bultfontein they do see more significant lags between rainfall events and the amount of time it takes to get out of the come out of the draw point. So this Gerard Keiter provided this case study. So this is Finch Mine in the Northern Cape, and it's also a kimberlite mine. I think what's significantly different here is that the host rock is banded ironstone at the top and then dolomite at the bottom, which do not produce mud. And in fact, they're very competent rocks, so there's been very little failure of the pit slopes over time. If you look at a satellite Earth image of that pit, you'll see you won't see slope failures. And then the kimberlite does break down and form mud, but because they basically draw all the kimberlite out, they talk about blue sky, so they draw the kimberlite to blue sky. There's no muck pile, essentially no muck pile, and they don't have any history of mud rushes. However, they have had a watering rush, so you cannot ignore that. So they had unseasonably high rainfall, which flowed straight into the pit, and in this case, the drainage was actually inadequate. So it was the drain holes were too small, and they couldn't transfer the flood water from 88 to 90 level. So there were no injuries or fatalities. There was a significant impact on production. One of the main challenges that they experienced there is that the footwall of the tunnels is mud. So when that filled up, was kimberlite. So when that filled up with water, it turned into mud, and that caused quite a lot of problems with trying to get back into production. I hope I've captured that correctly. I'll just walk you through some sources of inrushes. So we just got to. I quite like this. This came from one of the papers published in Caving 2026, which just shows you in tabular format how the contributing factors, so the historical draw, etc., fragmentation and the lithology, water and wet muck, and then your surface topography and how that influences it. It's even more complicated than that. Gerard has produced quite a comprehensive list of potential sources of inrushes, which I just asked Copilot to create a slide from this, and I'm not going to go through it, but just different sources on surface in the open pit, loose surface materials, muck column, muck pile and stopes, the undercut production and development levels, underground working and other triggers. And this is a work in progress. This is something that we're working towards. Okay, importantly, the risk assessment and the management of mud rushes. So we've seen Jarek Akubek's flow chart now 3 times. But that's because it's a very useful flow chart, and that highlights the sources of fines and sources of water entering the muck pile, and is there mud forming potential or not. So there are quite a number of mines around the world, like Finch, that just don't have mud forming potential, and but they still potentially have a water inrush risk. And so just in terms of the cave geometry, I tried to explain that a little bit earlier when I showed the evolution of the cave and then the schematic through New Afton mine. So you can see how significantly that affects the risk of mud rushes during the life of a mine. And then he suggests that you should do a mud rush risk analysis, implement the controls, and look at monitoring and preventative measures, and then safety, and consider the safety and economic aspects. This is actually from El Teniente again. So these are draw point risk ratings. So a lot of the risk ratings that I've reviewed are largely based on what they observe in the draw point, which is important. It gives you some indication of something imminent and perhaps a potential mud pocket that is close to the draw point. And it certainly is important and useful. This is another example. This is Alec Holder and Rogers and Bartlett and Harakata, my co-presenter. So this comes from their paper where they've collected information for each draw point, so looking at the moisture observed in the draw point, the tons drawn per draw point. So they've looked at the draw from the draw point in a few different ways to try and establish the different risk levels, and then looked at the dilution. So the dilution is an indicator of in this case potentially shales and mud forming material. And the percentage depleted. So new, as I mentioned earlier, the new block caves are generally lower risk than the more mature block caves. But what's really important is you need to look what's happening above you and look at the water and do all the things that Kim mentioned as well. So you need to be, and that should go into your risk rating as well. So if you're having challenges with managing the water, then obviously your risk goes up. If you have a significant rainfall event, your risk goes up. If you've got chimneys that are going all the way through to surface, accumulations of water on surface, those are all things that you need to take cognizance of. And that might affect several draw points or in fact the entire production level. Okay, so one of the challenges with these risk ratings is there's still a lot of uncertainty, and a lot of it is due to the composition of the muck pile. So, we have coarse rocks, muds, silts and clays. You've got air due to arching. You've got historical rat holes that are perhaps not visible on surface. So the draw history changes, and we can't see into the muck pile. We don't have technology to see into the muck pile, and if it's an old muck pile, that makes it considerably more challenging. So then external, we need to be aware of climate change and extreme events. As Kim said, we do have a lot of information on prediction of potential tropical storms, and that would increase your risk of mudslides and various other aspects. But because of that composition of the muck pile, the time that it takes for water that's entered the muck pile to come out the bottom and to report to your drainage systems and so on can be, it can vary. It depends how much void space there is in the muck pile and how permeable the muck pile is. So it can be, it can take a very, very long time. And if you're reporting red, so what we found, because you have a pit lake, for example, you say it's red, but nothing happens. So you carry on drawing and you carry on drawing and you carry on drawing because it's, and so there's a lack of belief. And I think this concept, we have the same challenge with prediction of rock bursts, you know, so how do we manage that? So getting the timing right, trying to understand when it's imminent remains a significant challenge. So I'll go through some monitoring and controls. So this is the mud rush diamond that comes from that work that was done. So you need to be aware of mud forming material, the water and disturbance due to mining and drawing, and then you need a discharge point for the mud to flow out of. So I like this picture that was, I hope you can see it. So this is the proverb of the blind man and the elephant. So I hope you can read there. So depending on where you look at it, your monitoring tool, you can get a very different interpretation of what's going on in the muck pile. So you need to, so each monitoring device and each aspect of your monitoring only tells you one part of the story. And you need to try and piece everything together to get a better picture of what's actually happening. So Kim has covered this very, very well. So, I mean, the water monitoring and management is extremely important. Reducing the amount of water going into the muck pile is critical, and that's and monitoring as much as you can is important. I think that the challenge that I have is understanding how much evaporates and how much goes into the muck pile because of the differences in porosity and permeability of the materials in the muck pile. So that does create some uncertainty. This is my colleague Peter Shepherd, who that's one of his favorite pictures. He's basically saying you can't just put a sign in and tell the water to go somewhere, go where you want it to go. so you have to have the right measures in place, and you have to have the right measures. You have to have systems that actually do work. So having the right drainage systems, the right stormwater controls, the right risk management. I think this is quite an interesting concept that was presented at Caving 2026. So this is from Filex Putcow mine, where they're actually backfilling inside the cave subsidence or the pit, which sounds scary, but they're selective over the backfill materials that they use, which comes from some of the roll from the subsidence, and they compact it. They compact it on top of the subsidence, and this is an ongoing operation that they do. And basically, they redirect the water. So they have about 20 typhoons per year, and they originate from the Pacific Typhoon Belt, and their annual precipitation routinely exceeds 3,000 to 4,000 millimeters. So by filling it and controlling the subsidence strategically, they allow the water to run off instead of going into the cave column, and it runs off into a creek downstream. So they've got, it's in a very mountainous area, so the topography is quite challenging, and there's tendency for it to flow directly into the pit, and this is the way that they've managed it. And they say that they've prevented catastrophic mud rush events that were experienced in the mine's earlier history, and so now this is much better managed. An important aspect in this, again, comes down to draw control, because the picture that I show you on the right, cross-section through the column, if you have isolated draw and overdraw, then you're going to still create rat holes, and you're still going to have problems. And there was actually a session at the caving conference on the potential for backfilling. There were quite a few interesting papers published. This solution is not always possible. You don't always have access to be able to do this, so it's not a universally applicable solution. But I think it works pretty well there. I have actually visited the mine, and what I didn't point out to you, you can see there's an access road that actually goes over the subsidence area, which was quite interesting. We didn't realize that until we had driven over it. And we arrived during a typhoon, actually. We missed the peak of the storm happened, fortunately, when we were safely in our accommodation. But there were, this had clearly worked pretty effectively, because we did inspect it afterwards. So in terms of discharge points, on the left, I've talked quite a lot about the caving. We've got draw points, so that could be just due to the management of your draw and collapse of hang-ups. And then the second one I've got is the erosion piping and chimney failures. So that is quite a significant risk. So you think you've got solid rock between you and wherever the accumulation of water is, but it can actually erode away. So due to the water that flows through cracks. And then, of course, failed backfill bulkheads. Just on the draw control, I've got just a few comments that I want to make about some of the factors that influence draw control. So I've talked about that. So always we have high production targets, and then you have things that go wrong, and then that's how. So in a block cave, look, the reason that these chimney or rat holes are created is the easiest draw points are pulled preferentially. So if you don't have proper draw control and proper draw management, the tendency is that people will pull the easiest draw points to meet their production targets, and that's quite an issue. But you also have damage to the draw point, and you have to close off draw points to repair them. And that means that you have to change your pattern. You get hang-ups in the draw point, so you're not actually pulling anything out of the draw point until you manage to deal with that hang-up. So it's quite challenging. The slasher block caves that are used in Kimberley, you have to, you're pulling along a slasher, and you've got a number of ore passes or draw points going into the slasher, and you have to open and close them to control them. So controls are important. So when you don't have controls managing that, then that's when you run into problems and you create these chimneys and voids in the muck pile. So in sublevel caves, that's different. So I've stolen a picture of sublevel caving from the internet, so I haven't credited this one, but it's you can see you're retreating back on multiple sublevels, but on any particular sublevel, you've got you normally try to draw. If you draw the full height of your blast ring, you create a significant disturbance in the muck pile. It moves down. It moves down whatever your sublevel spacing is, so 25 to 30 meters. It moves down quite quickly. Whereas in a block cave, we generally pull from multiple draw points, and you nibble away at it quite slowly. So the impact on the cave is, on the muck pile, is a lot more dramatic in a sub-level cave. So you want, so if you want to try and manage, prevent the ingress of waste and potential mud, you need to create an ore blanket, which means that you need to draw less than 100% of the ring. And I know it's very hard to tell a miner that you must not take everything. You've got to wait for it, and you've got to collect it from the level below, so that you've always got this pile of ore sitting and protecting you from that material. So that's quite difficult to manage. You don't have flexibility. You can't go back and draw once you've retreated. And once you get to the rim, you know, you might still want to get some material. You have to think about that quite carefully. Okay, so that just shows you how important the planning and controls are when it comes to draw control. So that you need to have, you need to do risk-based planning. So you need to consider if dilution is your only concern because you don't have mud, then you might get away with a more aggressive strategy. But if you have more mud, you need to have a much more conservative draw strategy, and you need to manage it a lot more carefully. So building the risk into the planning process is absolutely critical. And the tracking of tonnage from each draw point. With LHDs, sometimes you have automated, some mines have automated tagging systems, so they've got a very accurate record of the draw points. And then you need to have contingency plans in place when something goes wrong. So this is the flavor, this is the new fancy technology that's been talked about quite a lot at the moment. So it's been trialed in a couple of mines. So this is muon tomography. So it's basically cosmic ray particles. So they come from exploded stars essentially, and they travel through the Earth. They travel through us and through the Earth. They're very small particles, and you can pick them up with these muon detectors. And if you put them at the bottom of the cave, they actually can map the cave, and you can get quite a reasonable picture. So far the applications, they seem to be focused on the breakthrough of the cave to surface and managing air blast risk, so you've got a void above the cave. I haven't seen any discussions on using it to try and understand the characteristics of the muck pile, but it should be able to do that because it measures differences in density, so it should be able to do it. And I did find some papers on monitoring of tailings dams and heap leach pads for using the same technology. So we must be able to use this to help us understand what's happening in the muck pile. One of the challenges at the moment is there's a long lag time between getting the data. So it's not going to provide you, it'll give you a better understanding of what's happening in your muck pile and how it changes, but it's not going to give you an immediate warning. So then the last, I think this is the last control I want. No, it isn't the last hole. So water retaining plugs and mud rush barricades. So on surface you'll see these on Chapman's Peak and various other things. We have debris flow barriers. So they're not designed to, they're designed to slow down the flow essentially, and then to stop the flow of the debris, to allow water to pass. And these are designed based on energy absorption. So that's something that we could consider installing in mines. On the right-hand side, we've got mud rush barricades that were installed in New Afton mine. These actually have drainage in them. Well, they serve as both as mud rush and air blast barricades. But you've got to strategically place them and select them. So Kim's point about not blocking off your drainage, you certainly don't want to cut off your drainage. You need to place them in areas where that serves as if there is a sudden inrush, you can do it. This plug has drainage in it, built into it and designed in it. The concrete water retaining plugs, that's a critical control that we use for water inrush controls. We've used them in South Africa for many, many years, and there's some really excellent work that was done in the 1960s on experimental design of these concrete water plugs that shows how effective they really are. I mean, they in the experimental plug, they retained 45 MPa water pressure. So these controls have their place. They shouldn't interfere with other strategies. So exposure management. So you've got to think about the affected area and the exclusion zone. So for tailings dams, we do, tailings engineers do dam breach analyses, and they look at the effect of that. So I haven't seen that type of work done. We can back analyze quite a lot of these accidents and get some sort of sense of what sort of footprint that comes out. But you've got, a small mud rush can still injure and kill people. And these extreme events, they could fill the entire level, or they could fill multiple levels. And that makes your exposure management practically impossible. So you have to have strategies in place to mitigate against extreme events. Remote equipment, many of the mines that have mud rush risk are using LHDs to draw. Remote controlled LHDs are quite commonplace in the mining industry, so that's quite common. The other activities, drilling, charging, and other activities that you do are generally not using remote equipment, so people are still exposed during that time. People still need to go in to do inspections, so you could use drones to mitigate that risk. And then the point about the timing that I mentioned earlier. So quite often we can tell you there's an increased risk, but we can't tell you when it's going to happen. And that's, I guess, that's one of the challenges that we have to work out. So the way forward, I think this is linking to what Kim mentioned earlier. So I agree with Kim. We need a guideline. We need to work together to develop this guideline. And I think we need to establish an international committee as well. I think there's certainly local South African work that deals with our specific mining methods and some of the challenges that we experience that could be done purely in South Africa. But in terms of these caving mud rushes, I think it's quite important to establish an international committee. So that would involve mining companies. You really need to have the people that are dealing with and managing the risk on a daily basis involved in that discussion, and then people like me and academics, and then the regulatory authorities also being part of that system. So I think it should deal with a collation of best practice, but I think we do need to address the uncertainty, so that will require some research. And then I think a critical aspect is, what is management uncertainty in decisions? So when you have a potential risk, I mean, most managers, if you say, look, I know you've got a problem, they will listen and they'll tell you what to do. But if you say, well, I think you might have a problem, they'll come back to you and say, how do I deal with that? And unfortunately, with the uncertainty, we have to start dealing with these issues in a much more conservative way, and that might mean stopping until such time as we've gathered enough information to be able to do that. So Gerard and I been talking to the Australian Centre for Geomechanics, so we'll tie up with Kim, and I think that as part of the establishment of that international committee. So we've also been talking to some international people to try and work on that committee. And I think that's the end of my talk, and I'm sure I've gone way over my time. I hope I didn't bore you. I hope I kept it and I hope there was some useful information in there.
It's interesting with the recommendations you've made now. I was reading about aviation, right? Yeah. And how for the past 40 years, the scheduled commercial flights, they haven't had any fatal. I mean, it's a different industry, also, dangerous, but there are learnings there, and one of the key lessons is learning from incidents, previous disasters, and also international standards. I think were two key pillars of how they were able to get to like 40 years of no fatalities. So definitely that's something we're looking at to assist us, with our zero harm journey with mining. And you've mentioned MRAC, MHSC, those are key stakeholders for us we're working with as well. They have a summit, coming up 17, 18 September. So part of those discussions, must include some of the learnings from your side, William. Yeah, so thank you. It was long but needed, Tara. That's what we need, unfortunately, colleagues. We need to be detailed in what we're trying to do, so that we find sustainable, solutions going forward. You can't be high level and touching on the top all the time, nice slides. So we have to get into the details and find the solutions, yeah. So thanks, William, thanks. Yeah, round of applause again, colleagues. Thanks, William. It was detailed. It's a day of learning. We took notes and learn from what's being said from experts, academics, engineers, scientists, collaborative effort to solve this problem. Colleagues, next I'm going to call Mr. Howard Marsden. He's joining us online. I think Howard is in Zambia or somewhere in Africa. Can I check if you can hear us, Howard?
I can hear you. Can you hear me?
Perfect. Yeah, thank you, Howard. We can hear you quite clearly. And Howard, we said you will be projecting on slides, right? So you can have control.
Yes, I'll do that. Just trying to get it correct.
Okay. All right. So let's
give me a
give
second.
Howard a few seconds to project. Howard is now technical project lead at Ivanhoe Mines. But he's shared learnings with us in the Minerals Councils. Learning from incident session. Some of you would have attended. I think we really appreciated those lessons, on the recovery. And it's good that you shared with us again today, Howard. Thank you for, taking time to be with us. Howard, are you in Zambia, Howard?
I'm in the DRC at the moment.
DRC, sorry, yeah. DRC, okay, all right.
No problem. Is the screen up and can you hear me?
Yeah, we can see your screen. I think it's quite clear. We see your cover page. I'll hand over to you, Howard. Please go for it. Thanks.
All right. Thank you very much. Then I will get going. So I think from my side, I'm just going to try and focus a bit more on the learnings from the recovery. And certainly I'd just like to thank sort of the MRS and Manus and his team in terms of that program. It was something to witness. Just for myself, a mining engineer. The video that William showed was actually taken on my duty at Cullinan, the Bulfontein event, and now at the Toitspan. So I think I've had over 100 mud rushes, mud pushes, and events that I've dealt with in my career. So seeing it from the other side rather than the theoretical side on the ground. Just quickly, what I'm going to cover is a bit in memory, rather than Kim and others just mentioning numbers. Mine have got names, and one of the tough things of holding the chair is having to tell family members, what has happened, and that it's not an easy thing to go through, and I'll get that in some of the learnings. I'll just give a brief overview of 890 and what happened. I won't go into too much of the whys. I'll then go into the recovery, what it took to recover, and I think some key learnings from the recovery, and then I think some suggested improvements from my side on the ground, and then a little bit of maybe a bit controversial from my side, just the DMPR and inquiry, and how do we find the balance between that and sharing learnings, and then just some gratitude and thanks. All right, so unfortunately, we did have 5 loss of lives. Here are the 5 guys. And yeah, very tragic to have to experience this, and as mentioned, to put a name to it, and a family, and wives, children, kids, brothers. It was a very tough thing to experience. There was a shift boss in here, 2 very skilled drill rig operators, and 2 assistants. So not your usual category of employees. As William and Kim alluded to, we had an event at Bultfontein. That was 2018. So from 2018, 2019, I'm not going to go into too much of this, but this is what we have done to manage the water. And I tend to agree with William here. It's a lot more complex, than a simple model. There's a lot of uncertainties. There's a lot of unknowns. But, we drilled an additional 95 boreholes on surface. SAP, nappy gel, in the Bultfontein pit, the pit pond did have some influence, so we threw nappy gel into that to dry up the Detroit span pond. We lowered the pan level. We did some old level drilling, drained that, camera and alarms and monitoring, quite intensive water management, pit bottom analysis with drone pits and analyzing that. We built some dams inside of the pit to catch the surface water, rehabbed all the old water tunnels, old level inspections, pump philosophy, and water on 890. And, water sample and analysis. And I'm of the view it's not as easy as simple as in theory. It is extremely complex. And to try and find the correct trigger point for each mine, each block, each thing is extremely difficult. And then the Kimberley mines do have quite a long history. So we extensively engaged with everyone we could who's still alive to get their view on a lot of the events, including Richard Butcher and co. And then spending a lot of time in the old caves. And one of the dewatering strategies was to keep, the water flowing and don't let it build up. So, there's almost a presentation on each one of those as what has been done. But even with all of this, prior to the incident, I was feeling relatively comfortable that we've done significantly more than done before. And actually, all indications were the mine is drying out, and it was actually looking very positive. This is just some pictures to go and show that. I don't want to go into too much detail here, but just the bottom left, in terms of the pumping, if you've got a graph over 10 years of pumping improvement, I'm not so sure it's so easy to say, where's the trigger where you've missed something. But certainly a lot of work gone on water management after the Bultfontein event. Then just quickly, 890. So just a background, it's a Deutschman pipe. Mining started in 1869. The first 180 odd meters dug by hand, then chambering, and since that 4-level caves. Let me just try and get my pointer here. If you can see my cursor here, so the first bit done on surface, and then 4 big caves, 410, 575, 760, and 870. And that's historical. And then we were looking at a very small slice just below 870, 3 sets of rings here, and really just doing some pillar retreats in the section view, and in the plan view, that's what we'd blasted a few rings, fully aware that there's an old cave above us, and really just taking out the slice and not taking anything else. So quite unique from that point of view, not doing any caving, not doing any loading, just taking out a relatively small, isolated bit of the mine. And then just prior to the accident, there were 14 guys underground. The level above, this is their location, 870, and 890, this is where we had the guy sitting. And as I said, on the shift, we were loading the rings, and we were blasting development at T3. ST7, Bosvark, if you'll see it's called there, was on charge at the moment. In the workshop, battery machine, and the feedback from that operator, all dry, no changes, and certainly no warnings anywhere on the underground environment. So the event, 17th of February, just after 52 past midnight, significant air blast followed by flooding, rock, and very little mud. So everyone defaults to calling this a mud rush. I think this is slightly different. very large fenceable lava rocks, and 70% of the material was waste lava rocks. The power, the communications, return airway, pump station, compressed air, water line, second escape all knocked out. And just to see the damage, which is done, a UV machine moved about 80 meters and ripped in two. 3 drill rigs destroyed, and then there was a second rush of water after we'd started loading about 180 tons to try and recover. In total, 450 meters of tunnel was filled, about 9,000 cubes of rock and mud, and then we had to open up 305 of that for the recovery, and up until the point of the recovery, 48,000 cubes of additional water. And at this point in time, the last time I had there, 25th of June, still additional water coming through. So then just on plan view, again, I'll use my cursor. So on 890, the hatched area in black, that is the rings that had blasted. The orange was the extent of the full mud, and then the blue, the extent of the water. That was at 890. On the top level, mud had come through out here, and this dark orange closed up the second escape and the ROW, and then water come out on both sides, a significant amount of water on 890 and on 870. And just to try and put in some context, some of the photos. So here's the water coming through, the end totally closed up. This is sort of at the back of the WA here, big rocks in the water. This is the roof of a bolter, which still hasn't been recovered. Bolters sitting in this area, very far from the event, sort of the furthest part. And then just, the main tunnel there totally closed up with very coarse rocks and then free water running outside of it. Just a bit more pictures. I've got quite a few video clips, but I don't think they'll share properly, but just this is snaps of the video clips on 890. Driver in the dump truck was parked. He started going, saw the air blast, and very quickly water. And you can see the sort of the size of the big rocks coming through. The tunnel in front totally closed up, and the water running for quite a bit of time after the event. Proto got there relatively quickly, which I'll get into now. But significant amount of water quite far away. You can just see the water that is coming through, and it rose significantly in height and continued for quite a bit further. So again, just a few more photos. This is the face. This is a 4x4 meter tunnel. Sorry, 4.5 by 4.5 meter tunnel, and you can see the size of the waste rocks that have totally closed it up at that point in time. On the opposite side, the water level rising, that's the grade line. And as I said, this is probably 600-700 meters of tunnel away from the working face, and another point of access that we've got here. Just for interest, we do have a seismic system on the mine. The seismic system did pick up an event quite far above. We're talking about down here at 890, quite far above in the old cave. So at this stage, we've not sure if it's related, if it's the trigger or not. It does seem quite far away. And very interestingly, no other noise was picked up by the seismic event. So certainly not caused by a seismic event. This is just a seismic event picking up a noise. As mentioned, this is not the point of this one, but at the moment I've still got 4 questions unanswered. The source of additional water. Certainly on top of the water, we believe in the last 6 or 7 years, and we still, to this point, don't know the additional water. The source of the lava, we know there's lava on top, but how did it get into the cave? What was the actual trigger? What broke and where? And then how did it get to us on 890? Above us, we have got a 300 to 400 meter of muck pile. So how did this water and waste rock get to us there? And then if you just see on this graph below, the events happened over here, very normal, very static day-to-day water, huge amount of extra water that we've pumped based on the pumping capacity. And then even down here in June, July, we're pumping significantly more water than before. So is it just the tail of the event, or is there another source that we haven't got in? And just some analysis in this table here. The blasted footprint is 500 squares. 70,000 cubes come out. At the moment, I've done a bit of an estimate. I think there's about 100 meters of void to cause that air blast. These ones are all then showing, it should have gone to surface. And at this point, we haven't seen any influence on surface, so very unlike the Bultfontein event. This is my Y analysis on the right-hand side. I'm not going to go onto that now, but there's multiple sources of water, multiple sources, but at the moment, nothing is making sense. A bit of a sketch to me what could possibly have happened or some mechanism to have happened. As you can see, we just really blasted a few rings down the bottom on 890. Somewhere there must have been a void, and I'm assuming around 100 meters. Very difficult for me to conceptualize that. This block was last mined in 2000. It was expected to be quite wet and sloppy. And certainly when we blasted these rings here, we didn't really see anything, but for there to be a void that size, 500 squares by 100 high in an old cave not mined for 25 years is uncertain. And then somewhere a plug of this lava rock and 60,000 cubes of water above it. But this is all inside quite a big cave. As mentioned, there's 4 caves, 410, 580, 760. So somewhere inside of this cave, we've got, this is what it looks like to be the dynamics, but none of those really make sense. So I'm not going to focus on those for now, but that's just some of the complexities of this event. So where I will focus now is on the recovery. Mud rush alarm was triggered in a minute. The team on the ground reported to the CCR in 4, and in 4 minutes they could confirm that there were 5 missing. And certainly that's one phone call that'll stay with you the rest of my career. Management and proto on site in 46 minutes, and then clearing the rest of the shaft took us 2 hours 20. Unlike a lot of the media and other accusations that we continue mining, and no mining has happened since then. Just from the emergency control room and mine rescue services, 78 teams on a rotation, 15 different teams, 485 proto members, and 14,000 hours of proto work. Drilling, this is just a summary. I'm going to go into those in a bit more detail. Drilling, we try to drill 5 holes to the last known location. If there was air and we could make contact, then we would have had a different rescue situation. We had a master drilling on standby to drill a hole and recover. That drilling was completed on Saturday, and unfortunately all of that was certainly no pockets of air, no sign of life. In fact, quite a lot of positive pressure water coming up those holes. Pumping and power, we actually installed 31 additional pumps installed and or replaced, 2 additional drain columns, and as I said, until the point of recovery, 48,000 cubes of additional water was put in, and power really got knocked out and reconnected it a number of times. In terms of the loading, and again, if this was a traditional mud rush with fines and a lot of mud, I don't think we would have been able to load. We could only load because it was so coarse. 18,000 loads, 17,000 tons, 5 machines. Unfortunately, none of them survived the operation, and we opened up 305 meters of tunnel to access that. The picture on the right here, you can just sort of see, so each shift we were coloring as we were progressing. I'll go through in a bit more detail, but it was certainly an almighty effort, and I will thank the MRS at the end again, but I really believe we have a very professional crowd of volunteers working in our country. All right, so just quickly in terms of the drilling, so just some of the plans and sketches of the drilling. Last known location, we have 4 individuals here charging the development end, T3 North. 1 individual over here on the development drill rig. We did have a witness who confirmed. A witness was here who managed to get away, so he was actually sitting here at the point of time. And then we drilled these 5 holes into the last known location from the level above through the sections, and you can then just see water coming up the hole. So first part of the recovery was to try and get to them, establish if they were still alive, and unfortunately, this confirmed it. So on that Saturday afternoon, sitting down with the families is probably the next toughest thing I've done, to say that at this stage we don't believe there's any chance that they could have made it. Just from a pumping point of view, the whole schedule of how many pumps we had to put in, but it came on, and this was then our pumping capacity. Managed to get, took us 6 or 7 days to get to the peak pumping, and then we started to get on top of it. But as I said, 48,000 additional cubes pumped in a very short space of time. But just this will give you some of the feeling that we had to do, proto waist deep in, trying to get the pumps in, emergency lines, pumping it out. Your whole system got knocked down. So the first week or two was really just trying to get the pumping that we could start accessing, and then that we could start loading. If you look at the table below here, this is just the scoops that it took to get it, the ST14, ST7s from the west and then the east. And then, sorry, that color right at the end, after all those machines couldn't make it, we took a machine out of recovery to do that. Just some of the photos, the size of the rocks. This is the ST14 loader, and there's quite a few that it couldn't pick up. Here's another couple. So really, quite unique in terms of massive lava that's sat in there. And as I said, we really battled. I'll go through the learnings just now in terms of loading. Started to load right up front. We had a second rush of water. We only got the water under control to start loading over here, and then we could commence loading with water continually coming at us through this period. This is just one of Manas's slides on the 17th, but just as we were tracking it, this is where we had loaded out at this position on the 17th. We're sitting here, not sure what is happening in front of us, but knowing that we have to go to that last location over there. And then running out of space, we closed ourselves in, we backlashed ourselves behind as we went. So quite a difficult situation to be in, to actually try and get to the individual safely. To some of the pictures of loading, there's a 4.5 by 4.5 meter tunnel, rocks taking up the whole tunnel size. Drill rig that had to cut, blast, move out of the way. And then I'll come to just later, there's the dump truck from the other side. We actually used this as a bit of a temporary dam, but unfortunately that burst. And then putting on tires on the LSD sounded a very good idea at the time, but when you have a puncture and you've got to change that, it really added quite a few days to the program. Again, just a little bit more feeling some of the faces. So very coarse rocks as we're loading. And then this is now climbing on top where the water was still coming. A very thin layer of mud on top, a bit of fines, and then the coarse rock underneath, obviously, as it's flowed through. All right, so the recovery, the first miner we recovered after 21 days. He was 30 meters from his last known position. I'm going to cover in a bit more detail. And then the other four were recovered where we expected them to be 2 days after each other. This photo at the bottom left here is actually on top of where the last four guys were. They were underneath here. And yeah, just to see moving some of that stuff around really made it quite messy. All right, so some of the key issues from our side, all power and comms was tripped. Very difficult to restart all of that. Then we had a fire on Gugu. Gugu's the dump truck, MT42 battery. Got covered in water, and then we had 24 hours of fumes. So that was the only time the proto teams really had to use their sets, but we had to evacuate everyone. Very tough. And then we really didn't know what had caused it, what's up front. But every time we sort of loaded a scoop or two, we didn't know what was coming. Continual water. There, the guys were busy charging the development end, so quite a lot of discussion with Manas when we get to there, how far did they get to? Did they charge? Was it connected? And how do we approach that closely? Mid-month measuring, where was the actual face, on the plans that we've got, and where they were is quite different. As mentioned, secondary blasting of big rocks. When you're in a proto environment recovery, as I said, vent is totally closed and blocked. You're doing this in a dead end, very difficult. And also, where are the explosives? Miners, quite difficult. Removal of the TMM, as mentioned, we had 3 drill rigs inside of the muck pile. They don't load out so easily. And then even though there was not much mud on the big picture, all the mud that we had definitely messed up all the settlers, pipelines and pumps, and quite a lot of those had to be changed out in this period. Temporary dam burst at 890 that set us back a day or two. And then the TMMs, you're loading in an emergency environment, you're trying to, in conditions that you would normally not load in, and just spares and diesels, workshop tools, to do any maintenance. Stupid things like TMM keys missing at lost proto team, hand to the next proto team. They've gone, somebody borrows it, puts it down. All your systems go out the window in this sort of an environment. And then the TMM availability, one LDV, it got broken 4 times. It's the only route in and out. So it just makes the recovery very difficult. And as I mentioned, ST14 flat tires, we had to take the chains off, tire off site, replace back on site. A flat tire ended up being a 24-hour delay. And then as you're moving around this mud and wet mud, it makes everywhere else quite a bit wet and difficult to manage. We tried to hoist the ground, it just was too muddy to do that, so we actually choked the ground handling system, and then we had to find another place to tip. And because it was a recovery operation, you had to have a proto member in front of each bucket to check and make sure we didn't accidentally load anybody and miss them. A few TMM components were tipped into the crusher, and then we did experience some secondary flooding on 870. The main surface dam at 490 also had at one stage we sent too much water there and we flooded that. And then it sounds silly, but the surface water was cut off. All of a sudden now we couldn't wash the machines and look after the proto guys down there. I'll get to them just now, but if you haven't got water and proto guys are living in the water and mud, it's very difficult to really give them a safe environment to work. Compressed air was also cut off, and as I said, the backlash. Small thing, our proto team captain, he was offered a job, and as soon as he left, then we had to dissolve our team, and to this date, our proto team haven't been paid for this. And underlying all of this was the company going into liquidation, which just added another level of complication to this recovery. So the learnings from my side, I'm going to go now. So the people tracking, we had a people tracking in their last known location, as well as where they were. But the moment of the thing, the technology is wiped out, and post-event, they could have been moved anywhere. The TMM was moved 80 meters. Very fortunate that there wasn't any of the individuals in that tunnel in the direct line of fire. And closer to them, I'm not sure we would have found them. I've got a slide just to go a bit more on that now. And then let me go to that one now. So on the top left here, this is the last known location of one. So individual was standing here. Our witness was over here. So we had that prior to the incident. He heard the air blast and he managed to get out. When we loaded to this point, we couldn't find this individual. So now we're worried, if you hear something, is your instinct to get to the second escape safety, or do you go to your development end? We actually found him 30 meters further along, and our assumption at this stage is that he must have taken a step or two to the right, and then the event sort of swirled him there and he got stuck into his drill rig. If he had taken a step to the left or stayed there, I'm not sure we would have found anything of him. It would have been a lot messier. So, last known location, the technology all sounds good, but in this environment, the event could have moved him quite a bit further. The same on the other side. If I take to the top picture on the right here, this is where we'd opened up. We'd put in nets to make sure we had no movement from that side, but it was now getting quite risky going past this with the proto teams with 2 unstable ends here. This is the end that they were charging, but we were very concerned at this stage. Are they still there? Have they moved out? Have they gone anywhere on the side? If they'd been anywhere here, I'm not sure we would have been able to get to them. And with ourselves and MRS, we said we're going to go here. We'll look at those 2, but if they're not there, then it's probably becomes a Lily incident where you're not going to get them. So. Then with quite a lot of discussions, if an event happens, what do we tell the guys? What do we train them to do? Half the guys would say they go to development phase. Other guys, we sit still. So I'll get onto that. Then the recording in the emergency control room, as said, it was 35 days. We started with handwritten things, and there's a comment, it just gets, in the heat of the moment, what's written and what's recorded is very difficult. We really got to document and sign daily. Operational decisions, risk assessments, you got to be able to document all of that. It was chaos for a long time. And then, an incident documentation system. And what was very useful, we only found out afterwards that all the phone calls were recorded. So to put the pack together, you've then got the live recordings, which then suddenly join the dots to what was written down. And then I think one of the other learnings is what happens underground. Proto goes in, they go and change a pump, power, they go and do this. And very quickly you lose your design of what was installed. You've got to keep photos and videos of evidence, and then, record of change, what's actually been done. And from an operational, your system just falls apart in this recovery environment. You've got to put a whole new system of how we're going to manage keys, lessons learned. The emergency control room, very tough place to be for those 35 days. As I said, we had 18 different T's. How do we explain progress? No one to print, and we got back to really coloring on a penciling board where we are. And as I said, and I'm going to get into one of my suggestions, is manning an emergency control room. Typically, we just want a manager trained, but in this environment, if it's 35 days, you need a whole lot more than just one manager. The training, the skills, fatigue sets in. 387 hours worked by an individual in 35 days. And it's quite a hostile situation. Then just again, TMM. When you've got proto teams there, how do you operate? How do you do licenses, spares availability and tools, key control? It just falls flat, your normal system. Family in the media, very tough. I could certainly recommend you've got to have a dedicated resources for media, and then a separate resources for the families. We had daily comms with them at least, and then it was sort of said to be quite risky at the time, but we actually brought the family into the emergency control room. And I think because they were UMM and more of a family, and there's quite a lot of other family members in the mining industry, they understood. So maybe that was just unique. And then here, the recovery objectives should balance with the urgency of safety. So quite a lot of pressure during the rescue, especially from the DMPR. And it really, it was a very risky thing, and you've got to still take safety first. And to me, the proto captain on the face has to be able to make the call of what he's seeing. And again, it's very difficult if he's from another mine, doesn't understand any of the dynamics. So the understanding of what's happening, explaining in the control room handover is very difficult. Then stakeholder and underground visit manager, everybody wants to come and visit and see everything. You really got to try and limit that. We had the Premier and the Minister there, and unfortunately, everybody wants to go with, and it's just very disruptive to the recovery operation, and I think actually quite dangerous on another level. And then somehow, all your comms goes down. You need another set of emergency comms in this thing. The battery life and everything just wears down in that very short space of time. So my suggested improvements from this for us is emergency sort of fund for a recovery. My estimates, this was north of 20 million. And as said, when we went into liquidation, there wasn't anything whatsoever. And somehow that all mines contribute to a fund, the Minerals Council or MRS can manage. In my second one is that the Minerals MRS control room training, I believe it should be compulsory to all mines, but not just one manager, manager, mine captain, engineer, and GAS. We actually ended up bringing our engineering staff into the control room, and that made quite a big difference. And I suggest that you do the training on mine sites, part of evaluation, and do simulations. The number of what-if scenarios that we were thrown with is just absolutely mind-blowing, and you've got to make that decision, pass the instruction through to the proto guys on the ground. It's quite difficult. And then in my mind, if we want to do learnings and things, is somehow get a technical team for advice and assessment, impartial experts to come and sit. To date, I haven't had one question asked of me. There's been no real meaningful data has been gathered, and a fear of the inquiry versus learn for the industry. And I think that's probably the top point that I want to sort of bring up here. And then counseling to all, everyone thinks the proto guys are strong and tough, especially those directly involved in recovery. I can tell you it's not easy. The team on the shift, especially the key witnesses, I've seen grown guys, 4 or 5 days later in the toilets crying their heart out. It's not an easy thing, and I think we just missed that. And then also the management and the volunteers who put in extra hours and effort. Quite often, we don't think they need counselling, but I'm of the firm opinion that they all do. And then, just your personal professional cover versus legal appointees. And it's certainly a lonely and scary place, and I'm seeing fewer and fewer people wanting to take these appointments, and it's how do we manage that? Then just the DMPR and the data, they were there the whole recovery, which on one hand I think was good, but I'm not sure for what purpose. The Minister of Mines was there 3 times, the Chief most days in the week, and the PI and the SM. So lots of presence, and as I said, I felt a bit pressurized rather than assistance. portfolio committee was a disaster. Just making accusations that we're hiding, we're blowing people up, and it was really in the middle of the recovery. Myself and Manas took quite a few shots, unnecessarily so. I'm not sure how we deal with that. And as I said, continual pressure to speed up, which I'm not sure is correct. And then this is the one that I don't fully understand. To date, no instructions have been issued. We get instructions for notice board out of date, but major incident, just nothing. And then, in my mind, no real meaningful data has been collected. Submitted our 11.5, but no response. The Section 54 report we understand is being done, but not shared. And from a personal level, now we've got the Section 65 inquiry. There's a date for a start date, but nothing's happened, and we're now, quite a few months down the road, and we've got this cloud hanging over us. Then just from my side, as thanks, the emergency control room team, 3 guys in particular there, they were unbelievable. They stood through this. And I'd like to thank the BlackRock team. They sent a team to relieve us for a weekend. As mentioned, the mine rescue service and the proto team is just really unbelievable to see in action. Top right photo, they come in all their mois, nice. They get a briefing in overalls. When they come out, you can't recognize anyone. They're just 24 hours, mud, constant threat in front of them. They stank, muddy water, but the dedication, they just come back to say, sorry, Meneer, we just would have liked to have done more. Then I think from the Miners Council and the mining industry, the financial contribution, support and advice and pumps, and I must apologize, a few of those have not been able to be returned, but I think that was key. And then to me, the local community, all the meals and drinks, they came in, and then regular prayer sessions. We got bikers, a local church just coming to support us. And then some of the UMM guys went way beyond expectations, and a few of their copper teams, especially in uncertainty of liquidation, just chipped in there. So that's it from me. Thank you.
Howard, thank you very much. I think that was very, very good. It just gives, that day balance. We're talking mud rushes, the event itself. But I think Howard went into quite a lot of good detail about recovery as well, and recovery, not just mud rushes, any disaster or emergency events. I think a lot to think about. And also, Tushendra mentioned we had a very good session with the CEOs on Monday. And one of the key sort of contributions there was, that the MPR making reports available. I think that becomes very important as well as, different stakeholders, collaborating and the sharing of information and, investigations. I think William mentioned, going from investigations to managing the risk. I think it's a loop. I think we will still need to close, not just on mud rushes, but other incidents as well. So I think, as Minerals Council, as part of our advocacy efforts and partnership with the DMPR, I think those are conversations we need to be open in discussing and making sure we share what needs to be shared for everyone to learn. Colleagues, the next agenda item is actually not very long. It just talks to us as Minerals Council, myself and Tushendra, actually. That's what's written on the agenda. I don't know if Tushendra wants to come up there, but it's just to summarize, colleagues, we're in the process of coming up with, risk assessments in the form of bow ties, with the intention of coming up with critical controls, that can be used in the different operations and different types of mines. Dr. Kim mentioned earlier, we've had one session and, we only covered ore passes. And obviously we feel that is, incomplete, as, a huge part of the risk is block caving, as we've seen in today's discussions. So we've made a commitment, with our head Tushendra, that we'll be scheduling more sessions. covering more, bow ties in more detail, the block caving aspects as well. And we'll have, comprehensive outputs that will then be shared with colleagues. We'll probably set up, more focused discussions and engagements, just focusing on those bow ties, so that the industry can be assisted, So it's not just that, it's critical controls, but as it was mentioned earlier, some sort of guideline or leading practice document, I'm looking at my leader, Bra Stanford, there, from the MOSH team, if, in the future, some sort of, leading practice sort of guidance for the sector, so that we can be able to prevent, these types of incidents from taking place. Mud rushes are very low in sort of frequency occurrence. They don't happen often, but, if they do happen, it's disaster, as we've seen with, with the Kapa and the other incidents that have been shared. So that work needs to be ongoing, and we will definitely be in contact with all of the experts and subject matter, experts that have shared today, and mining companies, researchers, academics. It's a collaborative effort where everyone needs to play a role. Even technology companies, OEM suppliers, they also need to be in the conversation, be in the program, share what, we've spoken a lot about monitoring and sensors, that becomes a sort of technology area where we need to sort of listen also from the experts in the technology area. So we'll coordinate that. It's a coordinated response with everyone involved, all stakeholders, all discipline. And we'll have those discussions and share once we've at a point where we can share guidance to the sector, with international expertise as well, to guide, as a lot of incidents we're learning from are international. Yeah, colleagues, I think I'll just maybe stop there for now. And I saw online we've got, Albert's played a huge role to share. And I see he's online. I don't know if Albert van der Vyver can hear, and Dr. Kim as well in that session, if they'd like to contribute or share a few words with what we've done so far, looking at root causes, focusing on all passes, and also, consequences of what may take place, but also looking forward then and coming up with the critical controls. Albert, are you online? Or Dr. Kim, or anyone else, colleagues, that was part of our initial bow tie?
Yes, I'm here.
Yes, I'm not sure, Dr. Kim, if you'd like to maybe comment and share your thoughts around our process. And Albert, I saw he's on the call as well, if you'd like to share. Otherwise, please, Dr. Kim, if you'd like to share a few words before we move on.
Yeah, thank you. I think the bow tie was a very interesting approach and has value. As you already mentioned, that we concentrated on rushes down an ore pass. And I think we need to do one for the bigger picture for caving problems. And I think Alfred's probably the right person to share it, if he can share what was done on the screen. But in general, I think it's really important, particularly from Howard's presentation, that really showed the sharp end of mud rushes, and that there's a lot of variables that need to be incorporated into a study. And I think you've seen from everyone's presentation that there's been some good work done 26 years ago. There's been a little bit of updated work in 2018. But what I'd really like to do is get a concerted effort to use all the information with everyone involved and review what problems there have been and the causes, not the symptoms of the mud rushes. And let's attack monitoring the causes, not the symptoms. And as I have had big discussions with Deshendra, is move forward to a guideline, and preferably an international guideline, because we've got a lot of knowledge in South Africa, but there's also information for historic records in the older mining countries like Britain and Germany, and then information coming through from Chile and Australia as well. So that really would be my summing up, is that we've got the knowledge, we now need to turn it into a guideline. But on the bow tie, I think Alfred's the right person to talk if he's available.
Okay, no, thanks, Dr. Kim. We're probably, putting Albert on the spot. If he's here, he can talk, but if not, I think we'll just have a discussion with Albert on the side regarding the very good work he did for us in the bow tie, and then the next steps that we need to take in closing that loop, so that we, as soon as possible, we can, add value to the sector. That's what all of this is about. Yeah, colleagues, I think I'll close on that for now, and then, so the next session is a panel discussion. So what we'll do, we'll pull out the chairs, and we'll just ask our esteemed speakers today to come on stage, and also our speakers online, and then we haven't prepared questions. We want to make it as interactive and raw and real as possible, so we'll just allow questions. I see we've set aside an hour, we'll see if an hour is not too long, before lunch as well. And then if I can just ask, we take a 5-7 minute comfort break while we pull out the chairs, and then I'll just in that time ask the speakers to please come on stage while we set up the chairs. And then we'll go into the Q&A, which is, I think, the real sort of, meat of the session. It shouldn't be one way, it should be interactive. We need to, listen to the guests as well in how we, steer this response in preventing these mud rushes. I think it's an important session, colleagues. Yeah, please, let's take that break, 8 minutes, and then we start with the discussions at 12:30. Thank you, colleagues. Thanks. Colleagues, I want to see if our presenters online can switch on the videos. Dr. Kim and Howard. And then it becomes a hybrid panel, Chris, no?
All good.
With the colleagues here and the presenters online, if they can switch on their video. And my IT leader, if are we able to show if they can hear? Dr. Kim and Howard, can you hear us?
Yes, I'm good, thank you.
All right, yeah.
Yes, I can hear you.
Yeah, please, if you're able to switch on your videos, it will be great. Let's see if that works. And we can see
the video's on. Can you see me? The video's on.
Okay, just give us a few seconds, Dr. Kim. We can hear you very clearly. We just want to see if the video will. Yeah, we can see Dr. Kim right behind the other speakers, but I think that's fine. Yeah, yeah, and then I'm not sure if Howard.
My video is on.
Howard is
my video is on.
There shouldn't be a problem. If you can, Howard, are you able to show your video? But if not, it's fine. We can just hear your.
My video is on. I can see myself.
We see, yeah, no, it's fine. So it's me, and all right. So we're missing now. Okay, no, that's fine. I think maybe leave it on. Maybe let's not worry too much about the visuals. I think it will play itself out. Yeah. Oops. Okay. No, it's fine. I'm fine. Yeah, colleagues, I think this is, we haven't prepared any questions or, typically how panels are done. We just want to make this as authentic and real as possible, linked to our presentations today. So how I propose we run this, we'll just take maybe 3 questions at a time. And, it's good if the questions are directed to a speaker, but they can be open as well. And the panel can decide, we all answer or, how we do it. Yeah, but I think let's start, colleagues. Are there any burning questions? Maybe we'll just start with the first round, 3 questions. We'll take notes, as speakers, and then we just respond, cover those 3, and then we do another 3, and try and keep it less than an hour. I don't think we want to go more than an hour for today. So Akani and the lady are just helping. I see one question. Maybe let's take that question on my left. And if you can, when you ask the questions, colleagues, please, if you can, stand, and then we see you. You introduce yourself, who you are, maybe which institution you're representing if you want to, so that we keep everything on record and we're able to respond later on. Yeah, just your name, your institution, and the question you want to ask. Thanks.
Thank you, sir. My name is Puna Simmons from OASA. I've got 37 years underground trackless experience. And I've got a few only one question. It's for Dr. Tema. Doc, Mr. Tema, are you ready for me? Now, regarding your open cars trackless going into, look like from a high wall in, what precautions do you have, like emergency sumps, cross drains, settling dams, to look after the water in case of an emergency, especially the water coming from that big open area, normally in open cars going into a high wall? What did you have? You didn't explain to us your water plan underground. Although you talk about the water coming through fissures and certain places in your ground conditions, what have you got in place, like dams, settling dams or whatever, to look after flooded areas or flooded rain as well? Thank you.
Let's take, while Dr. Tema thinks about it, yeah, let's take another 2 questions and then we'll just answer. And then, yeah, we'll have another round. Who's closer? Akani, and then I saw the gentleman also here on the side. Yeah, we'll take 3 questions, and then maybe after that we'll take leadership there.
Thank you very much, the presenters in MQA. My name is Felix Manyanga from African Rebel Minerals. My question is direct to Dr. Is it Morton? I don't know whether I mistake it, because she say my question is, do we still need to do more studies on Madrash, or we need to consolidate what we have and push for compliance?
Colleagues, I hope that was clear. I couldn't really capture the question, but I hope Dr. Morton got the question. Dr. Morton, did you hear the question?
Yes, sure. It basically said, do we need more studies,
Okay.
or shall we just consolidate everything that we have?
Okay,
So
no, that's fine. Dr. Morton, please don't answer now, and then we will just...
Don't, okay.
Yeah. All right, thanks. Yeah. So,
good morning, colleagues. My name is Kitusitwe Mokhatla from Cementation Africa. My question is to Howard. And Howard, I hope this will not take you into the murky waters of secrecy because of the outstanding inquiry. However, I'm aware that between 2005 and 2004, 2005, I'm not clear on the date, there was a mud rush that also resulted in a fatality at Dutoitspan, but that was still under DBS. I wanted to understand, between the current area where mud rush occurred, when you compare the 2 areas of the previous mud rush and the current mud rush, how are they aligned? Is it within the same block, or is it a different position within the same ore body? And then the other question also to yourself, Howard, is to understand what was the time difference between the seismic noise and the first report of the incident. Thank you.
yeah, no, thank you very much, Ketsu. I hope Howard did, hear that question. And Ketsu has said, himself, there's an inquiry legal situation. So I think everyone is protected. I mean, it's for the intention of learning, But Howard will make that determination whether, is comfortable with, answering and accordingly. I think we're on the same page, Ketsune. Yeah. But let's maybe start with the first.
All right. No, thanks. Thanks for the question from the leadership from, you said NUM or WASA? WASA. Okay. No, thank you very much. And we appreciate your 37 years of experience in the industry. Because that's the learnings and the experience that we need at times like this. So in terms of the mine is an underground mine. So the first controls are on surface, keeping water away from the shaft portal area. So we've got surface trenches around the mine. Also the terracing work that we are doing as part of the construction of facilities, we are doing it in such a way that we can keep water as far away from the shaft portal area as possible. In terms of underground, we are still in development phase, so all our development ends are equipped with pumping capacity, with settler dams and pumps. So that's for the day-to-day, management of the water control. So in terms of mud rush, like I said, we've seen that the mud rush was coming in directly from, the rock mass, and that's what the work that we are doing now to deal with that. But in terms of water, we've got an underground drilling program, cover drilling program, where we know exactly before we get to those areas whether there is water or not, and then we can take precautions as we go to those particular areas. So day to day, it's being managed. This incident came, out of the explanation that I gave, but we're also working hard to be more preventative, even for mud rush type of incidents as well going forward. Thanks a lot.
No, thanks, Imran. Then I think Dr. Morton was the second question. If you can go ahead.
Yes, thank you. Admit this person. So the question was, do we need more research or should we consolidate? I think there's been a lot of papers written, projects done, particularly the De Beers one and the Simrak one, and there are other interesting items being developed in Australia and South America. I think the time now would be to consolidate what is available and learn from earlier incidents. With regards to research, once those incidents have been reviewed, then if it's necessary, we could allocate time to specific items. For example, Professor Dippenaar was particularly emphatic about the need to understand the mud. My consideration is there are so many variables involved in mud and water in rushes that the time is ripe now to consolidate that information. I believe that a lot of the studies that have been done have focused on individual variables, whereas now the time is to pull the whole picture together. So that's my recommendation. Consolidate the research that has been done into one document. Also, review all the regulations that are available around the world and find what people have to comply with at the moment. And then once we've done that, basically it's a desktop study. We can do a gap analysis and move forward, focusing on practical application to save lives.
No, thanks, Dr. Kim, for that response. I hope you covered, sir. And then over to Howard on the learnings from Ekapa.
Okay, so there's two questions. Was there previous mud rush, and if so, where and how close? And secondly, the time of the seismic noise. So on the first one, there was a fatal mud rush. Unfortunately, Mr. Muki was injured January 2005 in 870 Block Cave Drift 12. So it's the same ore body, but quite a far different block. We're currently, this event happened on 890 T3, so about 100 meters horizontally and underneath it. So not in the same mining method, and as I said, but there certainly was an incident in January 2005. In terms of the second one, the seismic noise, as we have it from the cameras going down, the incident happened at 0052. From the seismic system, they tell me 0051 was the seismic noise. So it appears to be a few seconds before the event. Thank you.
Thanks, Howard. If there are any follow-up questions, we can maybe take another round. Hopefully new questions for the other panelists as well. But if there's a burning follow-up, maybe we can exhaust that. Any hands? There's a hand. Is it a new question? Let's take a new question as well. We'll take 3 questions this round as well. Yeah.
Good morning. My name is Jacques Erasmus, Goldfield South Deep. Really great effort through the Minerals Council to host the day, and congratulations to all the speakers. So really, having spoken to the way forward post this event, something that Kim raised, and to yourself, Brian, although the event, the discussion bias today has been much about these major inrushers, William alluded to that as well. My take on the matter is that there are, when these major events happen, there's an outcry and it's in the public interest, and there's a lot of story going on about that. But unfortunately, the reality in the South African industry is that there are many ore passes, and these ore passes, the mud rushes that they cause are less pronounced, although there are many mud rushes, and luckily so that people are not injured or killed. How will those type of events also be taken into consideration when we are taking this matter forward? Because one would want to look at designs, orientation to the rock strata, and those type of considerations. Will that be done, or will we remain on the bias of these large events? Will that be the way forward? Thank you.
That was a good question. I'll take that as for myself. Yeah, so it's fine. We'll second hand.
Thanks. This is not an old question or a follow-up, but thank you for you, sir. You come to my point that I want to make. the on-mine Boxall ore passes, and I think my learner friend there from Ivanhoe Mines, Mr. Morden, they are also involved in the UG2 madrashes. In the Bushveld complex where we work, it's a very serious concern. And I don't think we finished with the madrash day of learning. I think we have to do a follow-up, ma'am, doctor. I don't think we finished, because we have to sit, like the previous speaker said, talk about boxholes in underground mining. Thank you.
No, perfect. I think I'll take that as more of a comment than a question, Puna, but well noted on my side, but we're welcome to comment on it. Sorry? Sorry?
Yeah.
Oh,
Yeah, that's important.
Okay.
I think we have a lot of small mud rushes that could create a big risk. Most mud rushes are unique, but each one has similar components to it. So it's still the concept of being aware of having are there mud-forming materials? What could possibly contribute to that? And in all passes, it's often backfill. It's backfill, and then it is different types of rocks that could break down and comminate and form mud-forming materials. And then usually it's mine water. It's sometimes groundwater, but usually, certainly in my experience, but I haven't examined I haven't done a research study on multiple ore passes. I think the principles remain the same. You've got to find out what your risk is based on whether you have those mud-forming materials, where's your water coming from, how you're managing it, are you keeping water away from your ore passes, that sort of thing. Yeah. And groundwater plays a role particularly. I mean, you might have an intersection of a structure with your ore pass, and then that could produce groundwater that you weren't aware of. So you really need to try and investigate the different sources. So yes, it is important, and I'm not aware of studies. It was covered a little bit in our CIMRAC report. We didn't go into it in a great amount of detail, but I think there's probably quite a lot of incidents that we can back analyze and learn from.
Yeah, thank you.
Yeah, maybe to add to that, because the academia and research matters come up here, and that is where everyone here should actually come together. And problems like this becomes academic research. Whether there's, like I did a review here to understand madrasas, and I think that's what you need here, to sit together, everyone who's involved here, bring your data, bring your problems, and get a university involved to do that. That's the only way I think you can really solve that, because it's a big problem, but working together.
No, thanks to our panelists for responding to those. Let's take another question from the floor.
Another question from Kitu for Dr. Morton. I think I must disclaim maybe before I talk. Howard, I was the mine overseer when that incident happened with Mr. Moki in Kimberley Mines. That's how I knew about it. And really what I wanted to understand is, remember, if you look on the eastern side of that 870, we even had Chinaman covers, we had remote control winch controls and all the lovely things. And the Mr. Moki incident happened in a newer portion of the block cave. I think that the point I was trying to understand is the new madrash that now happened. Did it happen in the eastern side where the intention with how we mined Ditoispan was that we'll slant everything to the east, and then the block on the western side was mined at a later stage. But even with that, we still had madrash in that new portion of the ore body. So I wanted to understand the orientation, whether it was more on the area that traditionally it was known to be a wet area, or was it in the dry area? And then another question for Dr. Morton. I know that in the past, I mean, people that go to Kimberley will know of the mushroom farm at the Big Hole. That is one of the things that was done as water management within the Kimberley area. And I want to check whether there is a write-up or anything on water management, because my understanding of your presentation, Doc, is that if we can get water away, we've dealt with mud rush in our ore bodies. Is there a proper write-up to say in this type of ore body, when you know 1, 2, 3, 4 about the water, this is the guideline that we're putting in place? Or is it something that you're hoping that with the international guideline, you will then incorporate a section just to deal with water management?
Okay, thanks, Kitsu. Yeah, I think we've got, we can take another quick, is there a question coming? Okay. All right.
Okay. Yeah, my second one, I think, is directed to the any member of the panel. I think from the presentations, no, to the any member of the panel, according to the presentation, which we saw today, most of these mud rushes either occur in old, where we are starting old workings, and then also at the bottom, where at the end of the pit, we go underground. So I'm asking now from a point of regulator, why should I allow underground operations beyond the open pit?
It sounds a bit more specific now. I thought it was open to the panel. Yeah, okay, so the panelists will answer to that. Okay.
Yeah. I think the risk of mud rushes needs to be taken into consideration, and you have to have water management in place, and you need to try and understand that risk. But, you know, there are so many mines around the world that have transitioned from open pit to underground. So it is common practice. So I think if you want to say, no, we can't do it, I think you'll end up stopping most of the mines around the world. I think the important thing is understanding the risk, and it comes down to those things. Do you have there are, and it's not just that there are mines that don't have, they're block cave mines that break through to surface, and they still have a mud rush risk. So it's not just pits. The pits could make things a little bit more complex that you need to understand. There are many operations that don't have a mud rush risk. They don't have the mud forming materials, but they might still have an inrush risk if water can enter the mine. And I showed you an example of a sand inrush as well. So there are all things that you need to think about. And so a lot of effort has to go into trying to understand the risk. If you've got an existing mine, most mines that have been operating know which rocks turn into mud, basically, and which give them problems. If you haven't experienced mud rushes before, it's important that you do quite a lot of testing to see whether you have the potential to form mud. The water controls become incredibly important. So all of those things are really, really, really important. And monitoring is a key issue. But I think this. We've got such a lot of material to work with, and I agree with Kim, we need to collate all of that. I think there still are some unanswered questions which I tried to raise. There are some uncertainties, like seeing into the muck pile and understanding what's inside the muck pile. That's quite a challenge, yeah. And that is, maybe that fancy Muon technology will help.
I just want to add one sentence quickly to that. So logistically, you swap one problem for another then, with slope failures and other things. So in other words, you'd indicate it with the problem.
I think I'll just also add that I think the biggest challenge we have, because, and even if you look at all the different incidents that we've had this year, the modalities are different. So I think, just going back to what William said and Prof. Kim said earlier, we need to get guidelines in place so that we can guide the industry in terms of the risk assessment work that needs to happen, so that we don't miss anything. Because, sometimes you are more biased to the risk, based on, what you know in that particular area. So I think one of the big outcomes from this engagement is to start the work together with the regulator to start working on those guidelines so that we can have a framework within which, the industry can all conform so that we don't miss any gaps. I mean, even the discussion around what about the water that's already underground? What about the dams that we use underground, to keep water? What about the management of shaft bottom, on vertical shaft? So a lot of things can cause a mud rush. So the important thing is to see how we can package a framework that covers everything. So obviously every mine will then customize based on their risk profile.
Okay, no, perfect. Maybe before we go to the floor again, Dr. Kim and Howard, Ketsu, I felt more of a comment. I'm not sure, Howard, if you'd like to comment further or respond. And maybe Dr. Kim to try and respond to Ketsu.
Yeah, I'll definitely have an offline coffee with Kitso there. Quite a lot's happened since he's left there. 26 years, quite a lot of things happened. So I'll have an offline chat with him.
Yeah. Okay. No, that's fine. Dr. Kim, on your side. Sorry. Yeah.
Yeah. Thank you. So the question was, is there any research on the effectiveness of water tunnels? Yes, there is. And one of the benefits of myself being in the industry for so long, we actually have a better corporate memory than some of the mines that have closed or head offices have changed. So we actually have a big database on the effectiveness of water tunnels, and that's one of the items we'd like to contribute to the start of these guidelines, which is consolidating all information. Just as background, we know that all 5 of the mines at Kimberley have had active water tunnels that made a big difference. That's why they were put in. And obviously Finch Mine, the 65 level, acted as a circular water drainage tunnel. And there are other incidents around the world where drainage tunnels have been used successfully. In my experience, it's not enough just to put in a drainage tunnel or drainage gallery. They have to be maintained. And they also have to have drain holes radiating out from them, which have to be maintained. But again, that goes back to my original comment, which was it's no good putting in a drainage system or a pumping system and then monitoring how much water you drain out or how much you pump out on its own. The target is to lower the water pressure. So it's absolutely essential to measure the target water level and see if you're reaching it, if you're close to it, for different sectors of the mine. So again, my emphasis on evaluating the older data and consolidating what has been done around the world is to start monitoring causes, not just symptoms. And I think the work we did on the De Beers research project in the 90s, that was all done at an analog level. And there's now numerical modeling capability to do that numerically and have multiple simulations, and also the opportunity to put it into digital twins as well, to do simulations and work out exactly what effort is required to reduce the head of water that causes such problems and results in mud and water inrushes. Does that answer your question?
Thanks, Dr. Kim. Thanks, Howard. Yeah, I think this round, maybe a general comment, maybe from Minerals Council side. Obviously, one day of learning will not solve all of our problems. We'd be fooling ourselves. It's a step in the right direction. It's one initiative that contributes to finding a solution, but it will never be a silver bullet solve everyone's problem. I mean, with that said, we'll continue with the work. I think the comments on all passes is well received. As I said earlier, we've started with the bow tie risk assessment, and we'll continue with that process, cover other areas as well. It's a systemic strategic problem. It's not just one root cause and then that will solve everything. So we'll do that industry-wide work that covers most commodities, as many companies as possible. But so one intervention won't solve everything, and I think to Puna's point as well, we need to continue having, these days of learnings. We learn, we go back to operations, we improve. In your own operation, you understand the risk much better than anyone else. I think it's a step in the right direction, and we will certainly consider all of these inputs as we structure our speakers, our program, what we cover, from the learnings of today. So we've assigned an hour. We can take maybe another another round, maybe another three questions, colleagues, and if you allow, maybe we can close for today. As I said, this is ongoing. It doesn't stop. Our doors are open, at Minerals Council. You can reach out to us at any time so that we find the collective solutions to address, most of our problems as best as we can. But maybe let's take another round. Who's closer to you, Kani? Is it 3 questions? Yeah, please let's go there.
Okay. Good day, colleagues. My name is Lydia Morake from UASA. It's more of comment, not a question. I just want the regulator to help us in this way. Meaning, sometimes you are mining adjacently to the old mine area or old mining. And then in that process, whilst you are mining towards it, you don't really know what had transpired. And because of the old area mining, the technology was not as advanced as now. You don't even have the layout of those places that you are going to mine. In that can cause that kind of situation that we are sitting in. The other one is, don't we have anything that actually can early detect or something that can alert us to say that, watch out or checkmate, something is about to happen? And coming to board and pillar, I know we are sealing some of the boards that we have mined. Then also, is there anyone or what does the regulator say when coming to those areas that we have already passed, however we are mining down, and then we have sealed? Those seals, are we trusting them to such an extent that it won't cause the very same situation that we are sitting in? With those, I'm saying, can the regulator please assist us? Thank you very much.
No, thank you very much. Well noted. I'm sure we have the regulator represented today in the room. Please raise your hand if you want to comment, if you would want to. Just Nonhlanhla and Aaron, I think that will be good. And then next, Shwakani? Yeah, thanks.
Good morning, colleagues. Stanford Malachi from the Mosh Learning Hub. My question is probably for Ndade Market. In your presentation, the Prof did touch on it slightly, acid mine drainage. I wanted to find out as to, because your mine has been sitting for a long time, and in the run-up to opening, did you do any studies around the prevalence and the extent of acid mine drainage, and whether in the analysis that you did after the incident, whether you found anything that has to do with acid mine drainage?
let's take one final question.
It's here.
Yeah, there's one person.
Sorry? Okay, thanks.
Good morning. My name is Ofense Mukoto, NUM South Deep. My question is that on the presentation that we have actually went through today, I just want to pose a question, this question to the experts. What is the cause of the sinkholes? Since it was actually stated that since we have gathered that most of the areas around the mine, they are dolomitic. Thank you.
Thank you. Question, well, panel noted that question. Is there a final question?
Yeah, it's from me. It's from me. I just need to test the waters to say, I mean, after every fatality and incident, there's a report that gets done. And how have we factored the learnings from those reports into what we want to do going forward? Or is it something that we didn't even consider to look at? Surely there are learnings that we can pick from the investigation reports, and what were the contributing factors that the investigation would have revealed.
Sorry. Right, no, thanks.
And that's for you, Brian. Eh?
Sorry?
That one is for you.
Me? Oh, okay. That's fine. Okay, so colleagues, I think let's then respond to this round. Yeah.
Okay, no, thanks. I'll just respond. I think our lady at the back just made a comment, and I think it just goes back to the risk assessment, understanding the risk adjacent to where we mine. And unfortunately, you're right, some of the old mining areas, there's not much information. Even the plans are not as accurate. So it just requires more prospective work before we start mining to understand the risk so that we can plan our mining methods, our mining directions, our inclinations accordingly. But just coming back to Ntate Malachi, the question around acid mine drainage. So, yes, from the EIA, the environmental impact assessment that was done, as part of the mining right application, it was picked up, particularly on some of these old dams, that there were signs of acid mine drainage. And also with the ingress of material into the mine, the samples that we took of the mud and the water was very low in pH, so it was very acidic material. So you're 100% right. So the area is highly oxidized, particularly close to surface, and the water is very acidic. So yes, it is one of the issues that we have around the mining premises.
Thank you. Yes, so basically on all three of those, what happens here with undermining is very much the same as with dolomites. So the restricted standard for development is housing, and the restricted for water is the drinking water. So anything that predates acts are exempt. So basically all the mining that's exempt from that, you are undermined, so no one has a clue of that. And that's the same problem as with the dolomites. So when it predates the 2012 standard, if your house falls into a sinkhole, it's gone. And basically the data there on percussion borers does not work. So for mining in Johannesburg, the house foundations and building foundations are built. So sinkholes fall under those buildings, and the buildings don't fall in. That's mining undermining. So for the dolomites, it's millions. So there's not enough money to fill that. And the biggest reason for that is my talk shear failure, like that wad falling down. So the holes are empty. If you've been in a cave, that's what it looks like under there. Okay, so that now for the undermining and the dolomites, for instance. So it's the same types of cavities that you have under the ground, and you have to live with that. So as soon as that open, it can fail, and both of them form sinkholes. Regarding the AMD, he was correct. So in other words, that happens also now after the fact. And that water also in the acid water, funnily, doesn't necessarily burn your hands. And people have this misperception it can be translucent. Okay, so that now the problem there is that the wit decants on the dolomites. So that acidity now, basically in the cradle of humankind, dissolves more dolomites. Okay, so the problem now is, and that goes back for the last thing now, like the undermine and everything is developable and mineable. Your cost of prevention is just more. Okay, that answers your questions.
No, thanks, Mr. S. We can take the next one.
Just to answer the question on reviewing incidents, investigations, that certainly, the SIMRAC research project, that was certainly a key component in that. In that research project, quite a lot of the information comes from there. There's very useful information in those. And that's part of what I try to get across in my talk, that information that we can learn from accidents that have happened, try to understand what the causes of the accidents were, what controls were in place, why, and why certain things were not identified, and what made it difficult for people to identify it, I should say. What made it difficult, and what can we learn from it, and how can we manage that going into the future. So there's a lot of literature on mud rushes as well. I've started using AI actually to try and compile my literature review. So I'm busy building that up. I think as part of this, that is certainly this group in the process of developing a guideline, the learnings from incidents, and not just incidents that resulted in fatalities. We need to learn from the near misses as well. How many mud rushes have occurred without being reported, and what do we learn from that? The guys that have worked on the operations have a great deal of knowledge. They've been living with these risks for a long time. We need to learn from them too. Yeah.
So perfect. Is there another question you want to respond to? I think sorry. Yeah, no, we're fine. I think maybe the regulator, there was something to the regulator, but I think it was more of a comment, Aaron, I'm not sure if you would like to comment or just note what's said, just to give an opportunity as well, because it's very important. If we can, please give a mic to Madam. Do we still have a microphone? This side, this side, Madam.
Okay, thank you very much. Just to add on the comment is that that's a big issue with regards to areas whereby they mine and abandon those mines. It's difficult to have control of those, because what happens is that, especially people who are mining under permits, they go and mine maybe for 6 months, 8 months, then they leave. And then next to it, then there is another mine. So you find that they don't even have a clear plan of the previous owner of the permits or the mining rights. So you find that there's no proper change management. So especially with the open cast. With the underground, it's more on most of the operation, they don't do proper risk assessment before they continue. They find that there are old designs that were there, or there's an old OPAS that is there that they did not identify. So you find that as they move or as they mine, they come across with those old designs. So it still goes back to doing proper risk assessment before you take over a mine, especially if it's a mine that was mined before. It goes back to the risk assessment. And sometimes with the open cast, what happens is that they'll mine and they don't do proper rehabilitation. And what happens, legal miners, they tend to mine and later on they come back and mine. You find that it's difficult also to control the mud rush in those areas. So what I can say is that it's also a concern to the regulators, but it's just a matter of sticking to the risk assessment. Thank you.
No, thank you. Thank you so much. I think that was excellent and very, very insightful, Sis Nontantla. And thanks for raising that question, to the regulator. They play a very, very important part, in solving our problem. Thanks for sharing that. I think we'll keep that in mind as well as we design other programs and then make sure that, everyone is covered. CGS, I know there was a project on old, abandoned mines, and I think they've got a lot of work we can look at the CGS. Yeah. Okay, no, that's fine. I think the last one, I'm not running away, Ketsu. I think you raise a very good point. I mean, I'll start by agreeing with you. You're supporting you that, investigations are very important. I think Howard raised it in his, presentation as well, your 11.5 investigation reports, is it Section 72 inquiry reports. All of those learnings and insights assist us certainly in coming up with, new interventions. In my previous life, Ketsu, I was a program manager. I don't know if that's what you wanted me to say for MREC. I was program manager for mining regulations for a long time. For example, the missing persons locator regulations came from the Lily Mine reports. So from that Lily Mine reports, investigations, from those, we used a lot of those outcomes from that report, and now we've got missing persons locator. That's one example of how going from, an incident to the regulator, investigating and outcomes shared, and now we've got regulations and mines are implementing, technology companies now are supplying the technology, so that, of course, that's one example of the importance of reports, Ketsu, very critical. It came up on Monday as well when we spoke with the CEOs. The chief inspector was there, and this was raised actually from, I think, AMCU raised this, where are the reports, please share, and the chief inspector was, receiving of that, and they will do the necessary homework to improve on that sharing, so I think I'll end it there from our side. Obviously, as Minerals Council, we take all the inputs and we improve in our other days of learnings and our other platforms. As I said, we have the Mine Health and Safety Summit happening on the 17th and 18th. We'll definitely take learnings from here and share in those discussions what you have shared with us here, so that all stakeholders are involved. Yeah, colleagues, I think let me thank the panel. Dr. Kim, Howard, I think you've been great. All of you, have done really well. And yeah, we'll just close it there, and maybe let's give a hand to the panel for doing a great job. Yeah, no, we tried. Yeah, no, thanks, colleagues. Yeah, thanks. We did a good job. Yeah, no, thank you so much. I think maybe as the panel, descends back to the floor, I would like to ask, Mr. Chris from Minerals Council, who will, give us his closing remarks and maybe some, way forward, and we'll take it from there. Probably, Chris, after that, we can probably maybe just close the session and have, go for lunch, and we can, it doesn't stop here, I don't even want to say goodbye or anything. We'll just share and just continue communicating with all colleagues here. But thanks to everyone, colleagues. Over to you, Chris. Thanks. Yeah, thanks.
Thanks, Brian, and good afternoon to everyone. And I'm happy you sat here until this time. I'm here on behalf of the Minerals Council, and just like to thank you. I'd like just to extend sincere appreciation to everyone who contributed to a focused and practical day of learning on this subject of mud rushes, water inflows, risk management, emergency preparedness, and industry control. This program reminded us, colleagues, that mud rush risk is a multidisciplinary challenge. It requires geological understanding, hydrogeological insight, sound mine planning, disciplined operational controls, reliable monitoring, and shared commitment to prevent harm. We know how many lives we've lost this year due to these mud rush inflows. And I mean, historically, we saw the presentation at how many lives have lost before. I would just like to thank Program Director Brian and the colleagues for organizing this insightful day, for steering the program and guiding the flow of the day. Appreciation to Dushendra Naidu for the welcoming remarks, which set the tone for the day centered on learning, collaboration, and shared objectives of saving lives. Colleagues, I would like to acknowledge Mr. Sipela Tema from West Wits for his technical overview of the mud rush incident at Kala Shellows mine. His contribution provided an important incident-based learning opportunity and reinforced the need to understand technical, operational, geological, and related conditions that can lead to mud rush events. The case study highlighted the importance of investigating root causes, recognizing early warning signs, and translating incident learnings into stronger controls, improved monitoring, and better decision-making at our operations. I would like to I'd like to thank Professor Matthias Diepener from the University of Pretoria for explaining mud rushes from an engineering, geological, and hydrological context. His was in a very academic perspective. His presentation highlighted the importance of understanding ground condition, geological structures, water pathways, rainfall effects, groundwater behavior, pore pressure, and the interaction between water and mud-forming materials in mining or in these environments. A key lesson from this discussion is that mud rushes becomes more likely where fine materials, water, and disturbance come together, and that prevention depends on knowing where water can accumulate, how it can move, and how it may be released during mining activities. We also express appreciation to Dr. Morton for sharing lessons from investigations and the evolution of mud rush and inrush risk management. Her contribution emphasized the value of structured investigations, learning from experience, and continuously strengthening controls as knowledge and risk understanding improve. The session reminded us that risk assessment must remain dynamic because the hazard changes over time as excavations advance. Water levels fluctuates, fines accumulate, ground conditions change, and new flow paths or pressure conditions develop. I remember saying the extraction points should always be below, the extraction point should always be above your water table levels or your water levels. Because if it's vice versa, it's bound to happen in due time. Colleagues, the discussion throughout the day also reinforced several practical controls and indicators that should remain front of our mind. Cover drilling information, water intersections, seepage, changing water levels, rainfalls, and recharge surface subsidences, weak or weathered materials, drilling practices, and the presence of fines in areas where water can accumulate. The use of drone surveys, geological and hydrological monitoring systems and integrated risk information can improve visibility of these hazards, but only when the information is reviewed, communicated, and acted upon timelessly. So we must be proactive. We must actually deploy these technological tools that we have in order for us to be able to understand the environments we are operating in so that we can put measures in place. Finally, I'd just like to thank the panelists that was here. The panel discussion gave us and participants an opportunity to connect technical knowledge with operational realities, ask difficult questions, and reflect on how the lessons can be embedded in daily planning, workplace examination, risk assessments, and the leadership conversation that we have on a daily basis. as we close, let us carry this forward, the shared message of the day. Mud rush risk can be reduced when we identify hazards early, understand water and ground condition, keep water levels under control, apply the hierarchy of controls, monitor the changing conditions, and act decisively on warning signs. Let this day strengthen our collective resolve to prevent recurrence, protect our people, and continuously improve the way we manage mud rush hazards across the country. This is the message that we just want you to take home. This is a continuous improvement. There's still a lot of work to be done. I mean, there's a lot of research that has been done on mud rushes and stuff, but we still have these incidents that continue to take their lives. So it's about the continuous improvement, a continuous fight. Colleagues, we have come to the end, and I know I'm between you and your lunch, but we did save some few minutes. I mean, we were supposed to eat, I think, 2 o'clock, but it's 1:30. Yeah. So with that said, I would like to wish you a safe travel home, and hopefully can take the message back to your operations. Lunch will be served at I think they'll direct you, but there's a restaurant at the food court there. That's where we're going to have a restaurant. Thank you very much, and goodbye.